Good morning, welcome back. Today you are gonna have like a little overdoses of optimal transport. So like 3 hours in a row. The good side is like you should enjoy as much as you can because it's the last section on optimal transport. So ask questions as much as you can because this is gonna have an end. So it's my pleasure to give the place to Simone. Simone, thank you.
Okay, so basically today we finish what I wanted to do yesterday. So we will start from the existence of the optimal map, and then we'll pass to the metric side and try to do a bit of a bit of work there, see geodesics, and if I have time, I will just say something about the sample complexity of a Wasserstein distance. So how quantify approximation of a measure with samples. Okay, so we start from the existence of optimal map, and we have to recall the Rademacher theorem, which I will not prove. You can find it in textbooks of analysis, which is quite simple. So it says that if f is a function from Rn to Rd, locally Lipschitz. What does it mean locally Lipschitz? It means that in every ball is Lipschitz, basically. So for every point there is a ball in which it's Lipschitz. So in particular also unbounded functions like x minus y to the power p or to the power n, it's still locally Lipschitz because maybe it's not globally Lipschitz, but it's locally Lipschitz. Okay, because this is a local property we see. Then what do we know? Then f is differentiable. And now you know that if you ask just Lipschitzianity, this is not true. This is not true. It can be not differentiable like the modulus. It's not differentiable in zero. But you see that, for example, this function is not differentiable in zero, but it's differentiable everywhere else, right? And what this is saying is that this is differentiable Lebesgue almost everywhere. Okay, it's a statement that says that basically in every point is differentiable, but this differentiability is almost everywhere with respect to Lebesgue. So the set where it's not differentiable has Lebesgue measure 0. And actually this is more or less a characterization, at least when the dimension here, when d is equal to n, then this is really a characterization. So if you have a set of measure 0, then there exists a Lipschitz function which is not differentiable precisely on this set. Okay. But this is the statement that you find. So the converse, it's much more complicated, and it's like recent research, so it won't bother. Okay, so we need these in order to show the existence of maps. And now we'll do this. So theorem, existence of optimal of an optimal map. We will see that in the proof, once you have proved that there exists an optimal map, then the map is unique. So suppose the cost, so we need something more on the cost. In this case, we need that the cost is L of x minus y, so it's a function of the distance, let's say, but it's just a function of x minus y, so it's translation invariant. It's something like really, I'm looking at some kind of distance between the 2 points. with L strictly convex. And then here we'll take mu, nu, which are probabilities on RD. So bear in mind here the space is x equals y equals r to the d. So this works just in Euclidean spaces. There are also version that works in Riemannian manifolds, but we'll do the easy one. Okay, with bounded support. So bounded support is a technical hypothesis. Actually, the theorem is true also if we don't have bounded support, but bounded support is needed for us because we proved duality just for Lipschitz costs, Lipschitz and bounded. And you see that this function, if you see it in all RD, is not bounded and usually is not Lipschitz, right? Even though it's locally Lipschitz, it's locally bounded. But instead, if we say they are bounded support, basically we can restrict this cost to the product of two bounded sets. And in bounded sets, this function is Lipschitz unbounded. Okay? Like every convex function. Every convex function in a bounded set is bounded and Lipschitz. Okay, so bounded support, this is a technical requirement. And this is not a technical requirement. We need that one of the measures is absolutely continuous with respect to RD, to Lebesgue. This is not the sharpest hypothesis. Actually, you can take mu does not charge sets of d-1 dimensional Hausdorff measure, but let's say this is the easy case. The other one is you know, other technicalities, and this comes really from this. So we see that this plays a role here. Okay, then there exists T from the support of mu to the support of nu, Borel, such that so mu is transported into nu, so it's really a transport map, and moreover, gamma optimal if and only if gamma is equal to identity T sharp mu. So what does it mean, this? It means really that, so once you get T, you have a map, and the optimal plan, so any optimal plan is of this form, which is unique, actually. What does it mean? It means that this is really the plan associated to the map T. Right? It's really the map, the plan like this. The plan which is concentrated on the map T and that push forward the mu. Okay. Special case. When we have the square, so the square distance, then T of x will be of the form gradient phi of x, where phi is a convex function. And this is what is called Brenier theorem, which somehow So Brenier theory is what Brenier theorem is what basically started then the third revolution of optimal transport in the 90s, and from that, so from that structure theorem, if you want, this is a structure theorem, right? So it's saying that there is an optimal map and has some structure, particularly since it is convex. You see that, for example, these should be also differentiable or almost everywhere. So it's not just a Borel measure, a Borel function. It's also something more. And from that, there has been all the theory of regularity for Monge-Ampère, which is the equation of change of variables, basically. And also many applications in the mathematical world. What do I mean in the mathematical world? Like, okay, using this kind of structure as a tool for showing other stuff, like isoperimetric inequalities, Sobolev inequalities, functional inequalities in the beginning, and then PDEs, ODEs, etc. So let's say this was a starting point from which then mathematician had fun with optimal transport. Okay. So, and why I'm stating this? Because to make full circle, right? So we began by saying what is the optimal transport problem at the beginning by Monge. So it's defined through maps. Then we relaxed because we noticed, okay, maybe there is not a solution there. And we looked at the optimal transport plan, so the Kantorovich formulation. Here we did everything, so you can show minimizers, you can do duality, etc. And now we're coming back full circle. In some cases, in good cases, actually the solution of the Kantorovich problem is the solution to the Monge problem. So in some cases, actually you have a solution to the Monge problem, which was not granted, and it's not apparent at all that it should have a solution, right? Okay, so proof. So start from the dual problem. So dual and primal solutions. So we take gamma bar, optimal, and mu, uv, which will be Lipschitz functions bounded on RD. So let's say we extend them in some way outside of the support. Optimal for the dual. Okay, so what do we have? We know from yesterday what? We know that first of all, u bar of x plus v bar of y is less or equal than L of x minus y. And then u bar of x plus v bar of y is equal to L of x minus y on the support of pi, of gamma. Right, so we have our gamma. We have our gamma bar, right? Thank you. An optimal plan. We have u bar and v bar optimal, a couple of optimal potentials. And we know that this happens, right? This is by duality. Okay. And now basically what we do, we will fix a point here, x hat, let's call it, and we will try to look at all the points which are all the points x hat, y hat, which are on the support of gamma bar, right? And the idea will be, we want to show that actually here there is just one point, okay? But we will need some conditions on x hat. This is not true for every x hat. but the idea is that it's true almost everywhere. Okay, and we take basically A, which is a subset of RD, where F is U bar is not differentiable. So in particular, Lebesgue of A is 0. This is by Rademacher. Rademacher theorem says precisely that this is 0, right? But now, thanks to this hypothesis, we know also that mu of A is 0. So it's not only Lebesgue almost everywhere, it's also mu almost everywhere. Okay, now fix. Let me see if there is something else. Okay, here we need also some other hypothesis, strictly convex and C1. C1 outside the 0 set, let's say, but we need also differentiability of L, basically. Okay, now fix X hat in the support of mu, but not in A. Okay, so we are in a point of differentiability inside the support of mu. And now we want to run, we want to understand and take y hat such that x hat y hat belongs to the support of gamma bar. Bear in mind, maybe this point does not exist. So you don't have anything on the support of gamma bar there, but we will see that those points, we don't care. What we want to say is that if there is a point, then this is fixed. Okay. Now, first of all, let me just do it for the square, because computations are easier. Then we will see how does it work in the general case. Okay, so basically we take an auxiliary function, f, which goes from so yes, okay, from the support of mu to R, and f of x is what? We take basically the difference here. So u bar of x plus v bar of y hat minus, I take the square, so this divided by 2. Okay, this is a function of x, right? So we fixed y hat, and this is a function of x. What does it happen to this function of x? So by the first point, so we have f of x less or equal than 0 everywhere on the support of mu. Right? And f of x hat is equal to 0. Right? So we have a function This is our x hat. And this function is always below 0 and here touches 0. And now what does it happen? Since we choose a point of differentiability for u bar, now you see that this function is thus u bar plus something else, which is differentiable in x, because this is a constant, and this we assume that this is differentiable, right? So what do we have? That f is differentiable by hypothesis. F differentiable in x hat. What does it mean? It means that actually first order condition holds. So the gradient of f is 0. So gradient of f in x hat, it exists and is 0. Right? And now we write it down. What does it mean? This. So 0 equals, and here we have gradient of u bar in x hat. This is a constant, so it doesn't appear. And then we have minus the gradient of this. Now, what is the gradient of the square? Is 2 times what is inside. So this is x hat minus y. Yes?
Sorry, why f the x hat of x hat is equal to 0?
The gradient, y f x hat.
Yeah.
So this is coming from this. Because f on x hat is precisely u bar of x hat plus v bar over y hat minus x bar minus y bar over 2 squared. But x hat y hat is in the support of gamma. And so we have equality here.
Okay, but we have L of x minus y.
Yeah. I said, so here we do the computations for
Okay, we suppose this.
for the square.
Okay,
right?
thank you.
Then we will
Okay.
see that actually it works every time.
Yeah, okay, thank you.
Okay. Is there any other question? Yes.
First, the first inequalities, minus of Lx min y, epsilon and the equal, the
Yes.
two dots,
Yes.
is a derivative for the last two theorem of yesterday.
Yes. Exactly.
But in the last two theorem, we have that C is lip bounded on, in this case, RD. We don't have this hypothesis. In
Yeah.
this
The
case.
idea is that so we restrict ourselves to just the support of the measures.
So in this case, is lip bounded.
So in this case, x is the support of mu, and y is the support of nu. And now x and y are bounded by hypothesis.
Mhm.
And so Lx minus y on support on x times y.
Yes.
Since they are bounded sets, this is convex, then this will be Lipschitz unbounded.
Okay.
Okay. So basically we do the duality on x and y, which are just the support. Okay. But the idea is that the differentiability holds because once you have a function which is Lipschitz unbounded on some set, you can extend it to Lipschitz unbounded on all Rn. Then we do care just about points which are on the support, but you can extend it, right? Okay. Okay, and now what do we do here? We can write y hat equals to x hat minus gradient u bar x hat. And this will be our t of x hat, right? What is t? T of x is just x minus gradient u bar of x. Right? And this, of course, we can see it as gradient phi of x, where phi of x is equal to x squared divided by 2 minus u bar of x. So, okay, the last thing we need to show in order to conclude the theorem, if you want, is that phi is convex and extend these to convex functions. So first, we see the extension to convex functions. And the extension to convex function is rather easy. So here we have L of x minus y. Here it's the same. Here it's the same. The only difference is here, right? So we do the derivative of this and you get the gradient of L. Right? But now the gradient of a convex function is monotone. What does it mean? It means that it's invertible, right? Because as if you want, it's easy to see it from the inequalities of Professor Villa the other time. So she said that if you do this, this is greater or equal than 0. This is monotonicity, right? Now it is, if it is strictly convex, here you have strictly greater than 0. But now from this, you can see that the gradient of f is injective, right? It cannot be that x is different from y and the gradient of f is equal to gradient of gradient f of x is equal to gradient f of y, because otherwise you would have this is 0 and this is strictly greater than 0. So it means that gradient of L is a convex function. Gradient of L is invertible, right? So here we can still do an explicit formula, but which is more complicated. So we write gradient u bar of x hat equals to gradient of L of x hat minus y hat. So we take the inverse function of gradient L. So gradient L minus 1 applied to this. This is still a function, and now we can write y hat equals to x hat minus gradient L minus 1 of gradient u bar of x. So you see that this is more complicated than the square. The square is rather easy. If you want, you can try, for example, and look for, I don't know, L of t, which is t power p, and see what is the inverse function in that case. So in the radial case, it's more or less, it's a bit easier, but you can do it in general. So it's not, you just have to know what is the inverse function, but we are mathematicians, so, okay, there exists the inverse. Yes?
No, y hat in the L x man minus y.
Yes?
On also this on in the definition of F.
Yes.
L is okay.
Yeah, there is y hat, of course. Thank you. Right. Okay. So we showed this. And we didn't conclude the fact that actually you are concentrated on a map. This is because we showed that if x hat y hat is in the support of gamma, then y hat is equal to tx hat. So if you want t, you can define it beforehand, because it's just something which depends on u bar. You define it beforehand, and then you say, okay, then y hat is always equal to t of x hat. And from these, basically, you can then show that, of course, it's concentrated on a graph, and that actually the measure is precisely the one given by this formula here. And so what do we understand from this? So two things. First of all, gamma is unique, because given any optimal Kantorovich function u and v, you are saying that gamma is this plan here, right? And so it's the unique one. We took any optimal plan and we showed that is equal to this one, right? But this is saying also the other thing round, because since this is true for every plan, then this should be true for every U bar which is optimal, right? So this is saying something also on the uniqueness of U bar, but this is not really unique. What we are saying is that basically, so gamma is unique, and about the uniqueness of U, we are saying that T U bar is equal to T U tilde for every U bar U tilde optimal Kantorovich function, Kantorovich potentials. But this is only saying that gradient of U equals to gradient of U tilde almost everywhere. And this is not saying really that U bar is equal to U tilde almost everywhere. It's saying that U bar minus U tilde is a constant in every connected component of support of mu. Okay, because this is true mu almost everywhere, right? So the gradient, if you have a function whose gradient is 0 on a set, now if this set is connected, it means that actually your function is a constant. But if it is not connected, so you are saying you have a function on two balls whose gradient is 0. Well, it might as well be 0 here or 1 here. The gradient is 0, but it's not constant, right? So you have to split the connected set, and then you have a uniqueness up to a constant, but it can vary from connected set to connected sets. If instead your support of mu is connected, maybe it's a ball, maybe it's the whole Rn, etc., then you have also uniqueness of potential up to the trivial change of coordinates that Augusto was saying yesterday. Sorry, not change of coordinates. Up to trivial change, I take U and I give you U plus C, and I take V and I take V minus C. Okay, and of course, this existence of the map works only on one way, because in order to do it the other way, we would need that nu is absolutely continuous with respect to Ladybug. Of course, if they are both absolutely continuous, then we get the existence of a map here, the existence of another map from mu to nu, and they of course will be the inverse of each other because of the uniqueness of the plan. So if I take the map here and they take the map there, they should give me the same point. So they are inverse of each other. Okay. So do you have questions?
I was wondering, we say that gradient of L is invertible, right?
Yes, gradient of L, yes.
But we need that it is invertible from Rn to Rn, or just from its image?
So we need, in this case, we just need it on this bounded set. So the bounded set created by all the difference of things in support of something and in support of something else. So for example, if you have mu which is here and nu which is here, so they are a bit far away, and you have L of x minus y, you can take also the modulus of x minus y. Why? Because on here, if x is here and y is here, you will have that this function is always differentiable because you don't hit 0, right? This is not differentiable only when x is equal to y. So if you have this joint supports, there's no problem. Okay, so the theorem holds for this if mu and nu are disconnected.
Okay.
Right? Okay.
Okay.
And no, but it doesn't work, sorry, because this is not invertible. So the gradient of this is not invertible, sorry. The gradient of this is like x minus y divided by x minus y, and this is not invertible.
Okay.
Because it sends everything to the,
but
so it's normalized, right?
How can we sure that the gradient of V bar is in the image of the inverse?
Sorry?
How can be sure that the image of the gradient of bar is sorry, in the domain of the inverse of the gradient? The gradient of L inverse.
By these. So
Okay, okay.
basically here you are saying that gradient of U bar of X hat is equal to gradient of L of something. And this is a condition that we found from this. So of course it's in the image of by calculation if you want, and so you just invert.
Okay, thank you.
And this of course is in the set support minus support. Okay, so maybe I want to do so the convexity of phi because I can talk about also should be easy. So we look again at the duality. So we want to do the max of integral of u d mu plus integral of v d nu, such that u of x plus v of y is less or equal than. Now let me put directly this, then you can generalize it at home. Okay, so as Augusto was saying yesterday, no, 2 days ago, one thing we could do here, okay, we want to maximize this. Okay, we can say we fix v, or we fix u, I don't know, and we want to maximize this just varying v, right? So in this case, what do we do? Okay, we can take, if you don't care about this constraint, okay, you can say, okay, I can take v which is plus infinity, right? Because here in this part, it's just a linear function of v. If you want to maximize it, you take plus infinity, right? You take v as high as possible in every point. Okay, and so it should be plus infinity, but you have constraints. So you have constraints, and in particular, you see that v of y is less or equal than something. So you cannot go really above and beyond what you care. So the only so taking into account the constraints, we want to basically take, if you want to maximize on v, we have to take the maximal v possible, which satisfies all the constraints. What is the maximal v possible? So we know that v of y is less or equal than x minus y squared divided by 2 minus u of x. This is true for every x in x, in the support of mu or whatever. Okay, so since this is true for every x, we can take the infimum over x, right? These inequalities are all true for every x, so it will be true also for the infimum. Okay, and this is what is called the C transform. And now if you look at the C epsilon transform, you can see that actually the C epsilon transform is an approximation of this. It's actually it was like minus epsilon integral of something, and what is inside is really what is called the softmax, which is again a way to approximate a max. See that there is a minus, it will be the soft mean, right? So the C epsilon transform is a way to approximate the C transform, and it's suitable for numerical purposes, of course, because you have an integral, and integrals are more or less fine to do on a computer. Instead, doing the infimum is much more complicated, as Silvia is showing to you, right? And in particular, this is not convex. You don't have any hypothesis on U, so it's very difficult to do this infimum, right? And so it's nice to have also this soft mean operator. So this is an inequality. And actually, you can take V. So V is less or equal than this. And if you take V equals to the C transform, of course, the C transform will satisfy this. Right? So V is less or equal than this, and UC is satisfies the constraint. So UC is precisely what we want to put there. Right? So if we maximize in V, what we get here is UC. And here we can forget about it, right? But in particular, let's look just at the optimizers now. This is, of course, saying that as in the talk of Augusto 2 days ago, this is saying that, okay, I can assume that in looking for solutions, I can assume that V is the C transform of U and vice versa, right? Because I'm saying, okay, I take U, then I take the C transform here, and then I take the C transform of my V here. And this will be something which is higher in value, so it's better, right? And still satisfies the constraint. So I can restrict myself to look at those. Why? Because again, you can prove that the C transform preserves some good, retains some good qualities from the cost. Okay. In particular, if the cost is Lipschitz, then this is Lipschitz. If the cost is bounded, this is bounded, etc. Like in the C epsilon transform. Okay. So we can assume that, and in this way, maybe you can prove that there exists a maximizer, as in the entropic case. But what we care about here now is that this says that if U bar, V bar maximizers, then U bar C, so V bar should be equal to U bar C on the support of mu. Because if this is not true, so we know that this is less or equal. If this was strictly less, then we could substitute V bar with U bar C and we get something higher here. Okay, so optimality condition. Okay. And now we want to look at this formula. So we know that V bar Y is equal to the infimum of X in X of this guy here. And now basically we want to prove something about this phi. And now this is, I develop the square. So this is X squared minus 2 times the scalar product for X and Y plus Y squared divided by 2 minus U bar of X. And now this is not depending on Y, so I can take it out. And then it's minus the sup of X in X. Of what? What does it remain? It remains Y X. So it remains this guy here. And then, so minus X squared over 2 minus U bar of X. Okay. And this basically we don't care, but we'll see why. And this is V bar. And now what we want to look is to psi of Y, which is Y squared over 2 minus V bar of Y. Right? In the same spirit of this. We change it variable, but it's the same. Okay. But now how to look at this? So now here, what we have to take this minus this. Yes? Yes. Okay, so this is equal to this sup here, right? If you rearrange the terms, you get y squared over 2 minus v bar equals to the sup. And now let me write it like this. So this is just yx plus beta x. I write it like this because I really don't care what is this. This is just an offset for me. Now what I'm saying here, this is, now this I call it Lx of y. So I want to look it as a function of y parameterized by x. So for every x, I have Lx of y. And now this as a function of y is what? Is a line, is linear, right? So what I'm saying is that I'm doing the sup of linear functions. What does it mean? So for every x, I have a line. And then I'm doing the sup. Right? And now I hope you can believe me that if you do the sup of linear functions, you get the convex functions. Okay? Actually, this is if and only if. Function is convex, if and only if is a sup of linear function. Okay? Prefer to do the picture. You can also show it, of course. Showing is like, okay, I take the almost maximize. No, I take every, for every x, I show that this stays above, and so you take the sup and it stays above. So now I don't care about the proof. I hope you believe me. Okay, so we did also Brenier theorem. Okay, do you have questions on this? Existence of maps and Brenier theorem? Okay. So we move to the next part, which is the metric side. So now I want to show that when I choose, so
thank you. Sorry, I just want to see if I understand correctly. Like, so the first part of was the problem of the existence, right? So the one where we show that we can invert the gradient and so on and so forth, right?
Yeah.
And then the second part is the construction to see that if I fix V bar, then I can always find one U bar. And so it's the one and only U bar. And so this is like the uniqueness. Am I getting this? I haven't quite properly followed why we did this last.
No, this last part, it was just to show that this function here is convex.
So, but this function is okay. And what we will need this for?
Because it was the structural part of Brenier theorem. So in general, we showed that for convex costs, you have the existence of a map.
Okay, and this is fine for me. Okay.
And this is okay. Moreover, if the cost is really the square, this is not the gradient. This is not just any function. This is the gradient of a convex function.
Okay.
So it's,
okay.
If you want, it's much more, right?
Okay.
It's saying that you don't have to look for your maps in all the kind of maps that you want,
But you can always
but
search for
you
this.
can restrict yourself to gradient of convex function, which are rather, you know,
Oh, okay,
rigid.
Okay, so this is like that. Okay, perfect. Thank you.
Okay, this is something more in the case we have t square over 2, right? And you can make similar statements for t to the p over p. So you can say something like, okay, this is not a generic function, but it's of the form x minus the gradient of some function to the power q over q or something like that. Okay, now let me just define these. So these are what are called the Wasserstein distances of order p. So it's the inf of a distance xy to the p, the gamma in pi mu nu. Okay, let's do it in Rn. Rd. Okay, so this is WP. So what I want to let you see is 3 things. So maybe 2 things. So WP is a distance on PP over D, which is just the measures, probability measures on RD, such that the P moment is finite. This is some, in a sense, a technical condition. We'll see why. And then there exists geodesics for this distance. What is a geodesic? A geodesic is when you are in a metric space. So if you are in a metric space, you have a distance between 2 points. What is a geodesic? A geodesic is a curve going from x to y, traveling exactly the distance that they have, right? How can we say this? We say that xt is a geodesic between x and y if x0 is equal to x, x1 is equal to y, and if I do the distance between xt and xs, this is just t minus s, the distance x and y. Right? This is a way of saying that this is a geodesic. Right? So if you take, for example, x1 half, x1 half will be a midpoint between x and y, meaning that the distance of x1 half from x is half the distance of the xy, and the same is true here, right? So is full of points for which the triangle inequality is actually an equality, right? So it's an embedding of the line 0, 1 inside the metric space. Okay, and in some sense, this is a minimizing length curve. Is a curve which is length minimizing in the sense of really length of a curve. In this sense, it's a geodesic. We'll just need this characterization. We won't bother for the other ones. Yes.
I try to connect my idea of geodesic, but why t minus s? I would have written only one parameter. Why? What do you mean with xt xs?
Xt xs.
Ah, okay. So they are two. Okay.
I take 2 points because if I take only 1 point and just say what is the distance between him and the endpoints.
Okay.
it could be that I have two geodesics, and I take xt equals to this up to 1/2, and then this.
Ah, okay, okay.
This satisfies the equalities and the endpoints, but it's not a geodesic.
Okay.
So I need this inequality for every couple TLS.
Couple. Okay, okay, I see. I see.
Okay. This, if you want, for technical reasons, but you're right that if it is a curve, then you need only the inequalities here. This is encompassing already the concept of curve, but I didn't want to bother for the concept of curve. Okay, so we could just say the geodesics, but geodesics look at this way, without saying that there is a distance, it's not saying basically anything. So we have to prove first that this is a distance. Once WP is a distance, then we will show that actually we have an explicit formula for the geodesics. Okay, so I want to show that this PP with WP is a metric space. So WP is greater or equal than 0, and equals to 0 if mu is equal to nu. So it's greater or equal than 0 is obvious because I'm doing the infimum of greater or equal than 0 functions. And equals to 0 if and only if mu is equal to nu. So if mu is equal to nu, we can take gamma, which is identity sharp nu, or we take the map, which is the identity, and this gives us 0 cost. So the distance between mu and mu is 0. And the converse also is true. So if WP1 mu nu is 0, then it means that x equals y gamma bar almost everywhere. So we need the existence of a plan. Once you have an existence of a plan, then this plan should have that function x minus y is equal to 0 almost everywhere because the cost is 0. And so x is equal to y gamma almost everywhere. And again, as we did in the last proof, it means that t of x equals to x is an optimal map. But then t sharp mu, which is equal to mu because of t is just x. This is also equal to nu, and so mu is equal to. Can do it in several ways. This is a way to see it. Okay. Then the other hypothesis that we have usually on metric spaces, which is you usually don't see it. You have to see that actually this is finite, because otherwise, if it is plus infinite somewhere, then you have what are called extended metric spaces, which are a bit of a pain to work with. And so we want to show that this is true. And here it comes the hypothesis of this PP of RD. Okay. And now why this is true? Because basically, you know, we say that this is the infimum of integral of x minus y squared d gamma. But now x minus y squared, sorry, to the p, we can use triangular inequalities. So this is less than x plus y to the power p. Okay. And now these, here we can use Jensen or means or whatever, but this is less than 2p minus 1 times x to the p plus y to the p. Okay, so the difference between x and y to the power p is bounded by if you want distance of x from 0 and plus the distance of y to 0, right? Problem is that we have power p, so we have also this term here. So this is less or equal than the inf over gamma of 2 to the p minus 1, x to the power p plus y to the power p in the gamma. Right? And now this, here now we have integral of a function of x with respect to the gamma. So this depends only on the first marginal. And you have the integral of y to the p only on the second marginal. Now this is equal because it doesn't depend on gamma anymore. 2 to the p minus 1 integral of x squared d mu plus integral of y, sorry, power p d nu, which is finite by hypothesis. We took mu and mu of finite p moment. Okay, and this is also an if and only if, meaning that beware that integral of x power p of the mu is equal to the Wasserstein distance power p of mu from the delta in 0. So in some sense, this is the largest set where the distance is finite, and you have the delta of 0. You have things with bounded support, let's say. This is just a comment, but okay. So what do we need? The last thing that you have to prove, which is usually the most difficult one, is the triangular inequality. So take mu nu eta in pp over d. What we want to show is that WP between mu and eta is less or equal than WP between mu and nu plus WP between nu and eta. Right? Okay. And this and this will descend from the triangular inequality on LP space. But we have to construct a special plan, basically. Okay. So from this definition, we have a plan which goes from mu to nu. I say it's from nu to mu. And from this plan, we have, from this definition, we have a plan which goes from mu to eta. Right? And these are optimal. And I want to construct, based on this, a good plan which transfers mu to eta. So the idea is to take nu as pivot and say, okay, I do the planning for mu to eta, and then I go from eta to, so from mu to nu, and then I go from nu to eta, right? Now, if I had transport plans, so transport maps, this would be obvious, right? So if I have a map here, T1, and then I have a map here, T2, I just do the composition. Composition will be something that goes from mu to eta. And this is actually this is actually what would give us this inequality. Okay, but in general, it's a bit more difficult. So I do first the case of maps. So we assume that there is an optimal map T1 and an optimal map T2. Optimal. Okay. And so what do we have? We have the WP mu nu is equal to the integral of T1 of x minus x power p in the new. Sorry, the opposite way around. No, okay, it's fine like this. Yeah, but works better in the other way. So let's say we have something like this. Bear with me, it will be mostly the same. And then we have this new eta, which is equal to T2 of x minus x power p d new. Okay. And now here, I do it like this because now they belong to the same space, right? I'm in LP of new, right? This is T of x minus x, LP norm of new. And this is T2 of x minus x in the LP norm of new again, right? So by triangular inequality, what I can say is that T1 of x minus T2 of x, LP norm of new, is less or equal than the sum of these two, right? This is equal to T1 of x minus T2 of x minus x, LP of new, and this is by triangular inequality less than T1 of x minus x, LP of new, plus T2 of x minus x, LP of new, right? So now this is equal to WP new, and this is equal to WP nu eta. So I would be finished if I show that this is greater or equal of WP of nu eta. Okay, and now I just write it down. And now this, here comes the magic of push forwards. So what is that? T1 of x minus T2 of x power p d nu power 1 over p. Okay, now I want to say that this is equal to x minus y power p d gamma hat power 1 over p for some gamma hat, and this gamma hat is just T1, T2 sharp nu. Okay, and this, if you want, is really by definition, right? So I have a map, so T1, T2 goes from RD to RD times RD. And in say giving a point x, I give you T1 of x, T2 of x, right? And now if I do it here, so gamma hat is this one, right? When I do the change of variable formula, I have to write instead of, okay, here maybe the best way to do it is y1, y2, the gamma of y1, y2. I have to substitute the couple y1, y2 with T1 of x, T2 of x, right? And so you get precisely this. Okay, so I'm done. If I can show now this is in a good shape, now this is really greater or equal than WP between mu and eta, if gamma hat belongs to this, right? Mu eta. Okay, but now this is just a method of definitions, basically, because if you now I take the first projection of this, so if I take pi 1 of gamma hat, This is just taking the first coordinate of T1, T2, sharp new. And now doing two push forwards is doing the composition. Now, what is the composition of the projection on first coordinate of these two things? It's just taking the first coordinate. And this is really mu. And the same way, we see that this is actually taking the second coordinate. And this is just eta. Okay. So in this way, we basically took an optimal a plan here, sorry, a map here and a map here, and we produced a plan between the other two measures, right? And this is quite general, actually, and is sometimes used for estimation of for estimation of distances, right? So you take a big centered measure, so a reference measure, and you take all the maps between of the optimal maps from that measure, which can be maybe a Gaussian, to all the other measures, because maybe for Gaussians is nicer, it's simpler. And then you can estimate from above the distance between any two measures by taking this pivot measure, and you say, okay, I do the map, and I do the LP difference of the maps, basically. And this gives me an estimate of how close are those measures. So you're saying, okay, the maps, the measures are closer than the maps are, right? So it's an estimate from above. Okay, this is for maps. For general plans, you have to devise a trick to say, okay, I have now a plan from mu to nu. And so it can be that I have some row of x given y, sorry, y1 x. So this is y1 given x. It's not a delta measure. And you can do the same with eta. Okay. And I have, this is row 1, this is row 2 of y1, y2 given x. And the idea is that here, what did we do? We coupled the point here with the point here, right? Here we have a little measure and a little measure. We have to couple them in some way. We just take the product measure, okay? We take these and we take the product measure. So the gamma hat will be something like integral in the nu of row 1 of y1 given x product with row 2 of y2 given x. Here you can take any coupling between those two. The simplest one is the product measure. And this works as well. This is again a function that works here. And you use basically the same inequality with respect to not new, but a more complicated measure. But the idea is basically the same. Okay, we proved that is a metric space. And now we see the geodesics. Then I will stop. So then if you give me 5 minutes more after that, I will show you one inequality about sampling complexity, because Ernesto said something at the first lecture which is highly related. But let's see how much time will take to do the geodesics. Okay, so we have our measures mu and nu. And we want to construct a geodesic, mu t. Okay, so what do we do? So this gives me an optimal plan gamma bar, right? So gamma bar is a measure here, which can be also not a map. and we have point X and Y. And basically, now you have to see it in a dynamical way. Okay, I have mu, I have nu. So every point X is going to a point Y, right? And you are transporting it. Now, what is the best way to transport a point X to a point Y? Going on a straight line, precisely. So if I want to do the midpoint between mu and nu, what I would do, take this path, and I take the half point, right? So this will be our midpoint. If you do the whole geodesic, of course, you have to take t times y plus y minus t times x. This is the constant speed geodesic in RD. Okay, moving on a straight line with constant velocity. Okay, and I do this for every couple of points which are in my plan. So what are we saying is that if you take the plan and now you take this ty plus minus 1 minus tx, which is something strange, which is tt xy. So this is a map, right, which goes from RD times RD to RD. Okay, we take points in the plan and we throw out a point in RD. And we basically want to say, okay, let's superpose all those points given the map gamma, right? Basically, we are saying, okay, everyone is going from the place here to the place here, time 0, time 1. And I say to everyone, go. And at time 1/2, I stop them and I see what is the distribution. And what it's saying is that precisely, okay, every guy, so the distribution of guys is really gamma, right? Distribution means so every guy has a starting point and a final point. So it's 2 parameters, x and y. And the distribution of my guys is accordingly to gamma, right? Everyone has to go from 1 point x to 1 point y, and the planning is according to this plan gamma. Okay, and then this will be the measure that that I will have at time t, right? So sorry, mu t, yes, exactly, the push forward of tt through gamma. Okay, bear in mind that so if gamma is given by a map, then when I write this, so mu t, I can write it just with mu in this way. So it's t, so 0, okay, t of x plus minus t of x, okay, sharp mu. Okay, this is another map, right? This time is from RD to RD, and this is the one interpolating from identity to the map T. Okay, these are similar but very different because one is in the plans and the other one is saying, okay, I'm taking x, I have to go to t of x. So what do? I take t of x plus 1 minus tx. I have already said what is y, basically. And so this will be my st of x, which is the optimal map between mu and mu t. Okay, so this is a good guess. Now we want to prove that is actually the right guess. And in order to do so, we just have to calculate what is WP between mu t and mu s. Right? But now remember what we did here. in order to estimate from above, it's sufficient to have two maps from a same measure, right? And then we do the estimates by taking that plan there, right? So in particular, this is less or equal. Now the maps, we have it. Those are the maps given as pivot measure gamma, which is in a different dimensional space, but we don't care, it's the same. So this is less or equal than doing tt of x and y minus ts of x and y power p in the gamma 1 over p. Okay, and now you recall the definition here, and you do the algebra, which is quite easy. I don't do it. This is equal to, and here is just t minus s power p, x minus y power p, 1 over p. So this is equal to t minus s wp between mu and nu. Okay, this was a good guess, and is actually the good guess. Okay, we have just an inequality, but of course, by triangular inequality, this is sufficient. Take the half point, for example. The half point is less than the distance half away from both endpoints, but by triangular inequality, the sum should be at least the distance from the points, so you have equality. Okay, and notice, now the nice thing about this is that, so there is a nice thing and a bad thing. So the nice thing is that given gamma, so even though we don't have a map, given gamma, we can say directly what is the geodesic. So this is immediately computable, right? What is the problem from the numerical viewpoint is that what we did the other time was that we fixing the location xn, y1, yn, we basically doing the histogram. So we fix the location and then we want to say gamma ij is what, right? Here, the natural way to see this is that we are moving points, right? So if I take x, I should put the same mass, the mass that I had in gamma ij, I should put it in gamma I plus yj divided by 2. So the measure lives in a completely different grid, right? And so this approach is very good when you are doing grid-free methods. So you didn't fix the location a priori, but because the other thing you could do is that, okay, instead of taking the histogram of my distribution, I take samples of the distribution. So I take delta of x1, delta of xn, right? I take some samples which resemble then the distribution when I look at them. Then in this way, now taking the sample approach, you see that actually now this makes more sense because you have really maybe a map because you have the same dimension. So it's in the set that I say that the first axis of the Monge discrete problem. And now it makes sense to take delta of x1, delta of yi, and doing delta in xi plus yj divided by 2, because it's a sampling approach if you want. Okay, so this is just a note on okay, now if I want to compute the barycenter, the midpoint, what do I do? Okay, so this is the most natural approach from the point of view of the geometry of the Wasserstein space. But usually in numerics, you fix a grid a priori and you want to do everything there. So in that case, it's more complicated and I won't enter in details. Okay, Okay, if I have 2 minutes, no, I don't want to do too much. I just say this. So this curse of dimensionality. About the curse of dimensionality. Okay, now take take mu probability on RD, and then take x1, xn, iid, xi distributed like mu. Right? Now, by the law of large numbers, what do we know? We know that if I do the sum of the delta of xi and I divide it by n, so this is a measure on RD, this measure weakly star converges to mu. Okay, what does it mean? That if I do, so for every phi, which is CB on RD, I have that this sum here divided by n converges to the integral. Right? Why is that? Because these are all independent variables, equally distributed, and so this is an average of independent variables equally distributed, and so the mean converges to the mean of the variable, which is this one, right? And also the convergence is also quantitative. This minus is constant divided by square root of n with high probability. Okay, just doing the inequality squaring, etc. Okay. Now this means that you are weakly converging because tested against any continuous function you are converging, and the convergence of the integral, so of the test, is actually pretty fast. It doesn't depend on the dimension, right? These are called dimension-free rates sometimes. So 1 over square root of n, and they come usually from something like this. Now, weak star convergence. Okay, we didn't prove it, but we say it. We said it. This metrizes the Wasserstein metric, any Wasserstein metric, metrizes the weak convergence on bounded sets. What does it mean? It means that if we have weak convergence, we have also convergence in Wasserstein space. Okay, so WP of, let me call this mu n. Mu n with respect to mu is converging to 0. Okay. And now the question is, do we have quantitative rates here? Quantitative rates like this. So this is a quantitative rate with respect to n. Do we have something here? And now here comes the bad news. This convergence is going to 0. So this is more or less. And I'm doing just in the case of mu is in between two constants and mu. So as density with respect to Lebesgue, and the density is between two constants on a bounded set. Okay, so this is really comparable to Lebesgue, right? If I'm comparable to Lebesgue, then this is approximately constant over n power 1 over d. So now this is not really in all cases. There are several special cases, so P must be lower than D, and D must be different from 2 and 1. But the gist is that this is happening. And why this is happening is rather simple, is what Ernesto said at the beginning, but the idea is very simple. You have to transport n points, right, to the whole support of mu, right? But now, what are those endpoints? What is the, given these endpoints, I have x1, xn. What is the distance of x from this set here? Right? Now, if x is one of those points, it's 0. But they are a few. So what I want to see is what is the average distance of a point from this set, right? Now this is actually greater or equal than 1 over n to the 1 minus d. Okay, and why is that? It's I do this inequality because in order to see why it matters. Because let's say I want to see what is the probability. So fixing x, I'm fixing x, right? And then taking x1, xn at random with xi, which are distributed according to mu. And I want to understand what is the probability that taking these n points, they are all far away. They are all far away from my point x. And now this is easy because it means that everyone is far away. So it is the probability of the intersection of I of xi, which is not in the ball of radius delta, right? But they are independent. They are independent, so the probability of an intersection is the product of the probabilities. And the product of the probabilities, they are all the same probability because xi are identically distributed. And so this is just mu of the complement of these to the power n. And now this is 1 minus mu of bx delta power n. Right? So the idea is that I want to say, okay, when this probability is high, let's say greater than 1/2, it's sufficient that this is of order 1 over n. Right? So this is greater than 1 over e if, let's say 1/4, if mu bx delta is greater than 1 over n. Because if this is greater than 1 over n, sorry, is less than 1 over n. If this is less than 1 over n, this is approximately 1 minus 1 over n to the power n, which is more or less 1 over e, which is less than 1/4. Sorry, bigger than 1/4. Okay, so this is the idea. You take the exponent should be equal to the one here, right? And now, what is the relation between delta and n here? Well, since we are in RD, this is more or less, this is greater, so I can take, use the fact that this is basically equivalent to Lebesgue, and so this is delta to the d times the volume of the unit ball times some constant. So I want this to be less or equal than 1 over n. And so I take delta, which is 1 over n to the 1 over d. So I'm saying that I can take delta, which is 1 over n to the 1 over d. So the probability that any point is far away, is is at distance at least 1 over n to the 1 over d, has probability 1/2. Right? And so I integrate these basically, and I show that this is at least greater than. And this is the bad inequality, right? So I have a rate from below. I cannot go faster than that. So the convergence is super slow. And you can have also the other inequality, but it's a bit more difficult. I won't enter into it. Okay. Sorry that I took too much time, but I thought it was interesting. So if you have any questions, please, yes, tell me.
The idea before of taking the geodesic on air to build the geodesic for the Wasserstein distance work also, for example, for manifold, for other spaces, or
yes, yeah. You basically you can lift the geodesics from the space to the Wasserstein space.
Okay.
It's just that instead of doing straight lines, you're doing the geodesic in the space.
Okay.
But it's the same, and it's pretty much you have a characterization of geodesic in the Wasserstein space that are forcefully like this. You have a plan and you have geodesics.
Okay, thank you.
So good morning. Okay, now it's working. So thank you everybody who survived until the last part of this optimal transport. So I'm gonna ask you guys a huge favor. So the feeling that I have is that I'm gonna to do this teaching at 5 a.m. So I really need your help to make sure that everything is in order on the blackboard. So also people online in the future can enjoy what is written there. So like the goal of today is basically do the convergence proof of the Sinkhorn algorithm. So in the practical section, we did some simulation. We use some pedagogical data of Gaussians. And we see that we were able to compute the optimal coupling for the entropic regularized. But we were lucky, we choose a very nice data that works well, or Sinkhorn algorithm converges in practice. So this is converges always, no? Can you give a hit theorem? So like before, like stating the theorem and going to the convergence of the Sinkhorn algorithm, let me just restate again the theorem that the proposition that I stopped last time. So, and this is also a way of recall the setting that we are working. So we have like X and Y Polish spaces. So complete separable metric spaces. If you wish, think that X and Y are like subsets of RD or even RD itself. We have C that in our framework is a bounded coast. I'm using row 1 and row 2. So row 1 is a probability in X and row 2 is a probability in Y. And we have epsilon is bigger than 0. So what is the proposition? So the proposition is the following are equivalent. Number 1, U star and V star are maximizers of the dual problem. Remember that we are in the entropic regularization of optimal transport, so entropic optimal transport. So this is equivalent, so if and only if V star is the C epsilon transform of U star and vice versa. U star is the C epsilon transform of V star. So this is also equivalent to define pi star as the exponential of U star plus V star minus C divided by epsilon. Then if pi star is defined in this way, then gamma star is actually a coupling between rho 1 and rho 2. And finally, probably this is too low, but then I'm going to send this blackboard on the top. And the last one, we have like the primal dual relation. So the entropic regularization of optimal transport, so the OT epsilon, is equal to the maximum of the dual problem plus epsilon, that is a constant that appears in our computations. So like this is basically, this proposition gives you like the complete characterization of the primal and dual problem. And in particular, like follow our approach. So we start with the maximizations of the dual problem. We completely characterize the minimizer of the primal problem. And we have the dual and primal conditions. So in particular, what this theorem implies, so this theorem implies that like the optimal coupling for the entropic regularization of OT is given by a gamma epsilon, that is a function A of x, B of y, exponential of minus c divided by epsilon of x and y. And by using the fact that pi epsilon is a coupling between rho 1 and rho 2, to compute pi epsilon reduces to solve the following system. So you need to solve, I'm writing directly because we did this many times. So I just need to compute A in terms of B. That is precisely what we implemented yesterday. The rho 2 and B is the equivalent, but now I put A. So, and this is called the Schrödinger system. So again, epsilon is given, C is given. To determine pi epsilon, I just need to compute A and B. Recall that A and B depends on epsilon, but I'm for dot charge the notation, I'm just writing A and B. So that's what we did yesterday. So we implement the Sinkhorn algorithm by alternate maximizing A and B. Clear? So let me put this on the top. So questions about the proposition. And like, so we are exploiting basically the point 3 and the equivalence between U and 3. And we get this. So now, any questions? Good. So now let me state, so I'm not going to prove the proposition now. I leave the proof for later. Let me basically state the theorem. That is the convergence guarantees of the Sinkhorn algorithm. So again, under the same, in the same framework, so under the same hypothesis, of the proposition, so what we have, there exists a sequence of scalars, so lambda n, so there exists a sequence of scalars such that lambda n AN converges to A in LP of rho 1 times root of LP of rho 1, and Bn divided by lambda n converges to B in LP of rho 2. So let's fix P between 1 and plus infinity, such that where A and B solve the Schrödinger system. Moreover, if we define gamma n by an bn exponential of minus c divided by epsilon, this converges strongly to a b exponential of minus c divided by epsilon in LP so let's call in this way. So where gamma bar epsilon is the solution of OT epsilon of rho 1 and rho 2. So the solution of the primal problem. So just to make this theorem consistent, so like basically the idea of so how we define the Sinkhorn algorithm. So we initialize A0, B0, as you wish. So for example, identically equals to 1, and we define iteratively A n using B n minus 1, and we define Bn with the an that we compute previously. So the statement of the theorem is let an and Bn be the Sinkhorn iterates. So when n goes to infinity, we have that an converges to a function a, Bn converges to a function b in LP, where a and b is precisely the solution of the Schrödinger system. Moreover, if you define pi n in that way, this converges strongly in LP to pi bar epsilon, and pi bar epsilon is precisely the solution of the primal problem. Okay? Check if the statement is clear, because this is precisely what we are going to spend some time to prove now. Yes, Andrea, the microphone.
Do you derive also a quantitative estimate, or the result is qualitative?
So you are very curious about the next. No. What we are going to do is like a kind of existence theorem,
Okay.
because we are going to rely on the kind of a priori estimates that we did 2 days ago. So like we are going to rely in a compactness argument. So basically the theorem is what is stated. I tell you that there exist A and B in the limit. So how fast this convergence go, the proof is not gonna tell us, and we did it to develop another type of machinery to do this.
Okay.
And but we are very happy to discuss on in particular. Simone has been working a lot on this. So you are sit next to the person who have done a lot of computations on this, on this regard. But you see that is a calculus of variation proofs of convergence. So we say that there exists, we use a compactness argument, and that's it. So other questions? Is the statement clear? What we want to do? So what I'm going to do something not super nice, but I'm going to erase the statement of the theorem, but we all have this on your notes. Can I erase it? And then I'm going to use what is on the top to do the proof. So I'm not proving the proposition yet, but I'm proving the theorem that I'm just erasing. So the theorem of the convergence. So is the speed okay, or I'm going too slow? Fine. So let's do an idea of the proof. So proof idea. And this is like the theorem convergence. So what is the idea of the proof? Let me probably divide the blackboard. So the idea of the proof is like quite simple, and like the important point is, so when you implement the Sinkhorn algorithm, you look to the Sinkhorn algorithm as a sort of a matrix scaling, right? You start with a pi 0 that is given by a0, b0, exponential of minus c divided by epsilon. And then in the first iteration, you fix one of the marginals. And maybe the other one, so the second marginal, let's say, rho 2 was not correct. Then, by the second iteration, you fix the second marginals. So basically, you were updating A and B, that you can be seen as like entropic weights, that guarantees that pi is actually a coupling between rho 2 and rho 1, at least approximatively a coupling between rho 2 and rho 1. So the idea of the proof of the Sinkhorn algorithm is do like a smart change of variables. So instead of looking the Sinkhorn algorithm as something that updates A and B in order to find the pi epsilon that is the solution of the primal problem. So what we are going to do is like we are going to write A of x exponential of u of x divided by epsilon, b of y exponential of v of y divided by epsilon. And we are going to substitute now u and v where there is a and b. So, or more precisely, so let's put a n, I write un, bn, vn. So now, if instead of working on a and b, I work with u and v, you can verify that un of x is given by minus epsilon log of integral in y of exponential of vn minus 1 of y minus c x and y divided by epsilon integrating the rho to y, and vn is given by a similar expression, but here I use the un that I compute in the previous iteration. Probably at that point, you can recognize what those two expressions are. So basically, what you can see is that this, by definition, is the C epsilon transform of Vn minus 1 and this is the C epsilon transform of Un. So now what can we do? So using this change of variable, so let's rewrite the Sinkhorn iterates in a different way. So let's now define V2n plus 2 is equal to U2n C epsilon transform and U2n plus 2 is equal to just to n plus 1. And now I define 2n plus 1 is basically the C epsilon transform of the V, and then I keep exactly the same, 2n plus 2. I guess this is going to make the job. So why I'm doing this? Because now, thanks to the properties of the C epsilon transform, what we have is, we basically define a sequence that are monotonically increasing the dual functional. Etc. And we know, I guess, this appears also in Simone's talk yesterday, that those guys are bounded by the primal problem. So what we have here, so then we have like a monotonically increasing sequence that is bounded by a number. So the idea is now, so what is the main idea? So instead of looking as the Sinkhorn algorithm has a matrix scaling of gamma epsilon, where you update A and B, now you really want to look as the Sinkhorn algorithm has a block gradient ascent in the dual problem. That is like the key idea. And now we have two choices. Now what we can say, so thanks to a lemma, so lemma, previous lecture, we know that there exist scalars, lambda n, such that un minus lambda n, vn plus lambda n is less or equal than 3/2 of the norm infinity of norm infinity of C. And this is thanks to the property of the C epsilon transform. So we are assuming that C is bounded. So the boundedness of C, I'm integrating in Y. So the boundedness in X is transferred for the potentials UN. The same here. So I'm integrating X. So the boundedness of C in Y is transferred to the potential VNY. So in here we get the compactness. So the compactness that probably Andrea didn't want. So we don't get the rate because so we have like compactness of this sequence. And here you have two options. So to extract a convergent subsequence, because we have already the C epsilon transform that grants me this regularity. So we can do like in the proof of the dual problem. So we use Banach-Log-Luz theorem, and we get a subsequence that converges to, let's U bar and V bar, and you can and you know that this U bar and V bar are in L infinity. But the theorem has stated I have the convergence in LP for every P. Say? Strong convergence in LP. Very good. So then what I'm using is one of the properties that you, I guess, ask some questions. That you say that we are using that like the C epsilon transform is also like a one Lipschitz compact operator between L infinity and LP. So I'm going to use this property of the C epsilon transform to grant that like there exists a subsequence. I'm going to use the same UN, so a subsequence UNK. So let's do this, such that UNK LNK converges to U bar L bar in LP of rho 1 and V NK minus plus LNK converges to V bar plus L bar in LP. This is because the C epsilon transform is a one Lipschitz compact operator between L infinity and LP. Anyway, you could get the same, but like the convergence in L infinity by just using Banach-Waloglu. So can I erase here at least this half side? So again, so I have like this, the sum or subtracting this constant, which is precisely the invariance of the dual problem. So in the end of the day, we also have that UNK plus VNK ln minus ln K, this converges to minus C. This converges to U bar plus V bar minus C in LP rho 1 and rho 2. So what remains to show, so what we want to show is that U bar and V bar are maximizers of the dual problem. Because if they are the maximizers of the dual problem, we know that they also A and B, that is given by the exponential of U bar divided by epsilon, and B exponential of V divided by epsilon, are solutions of the Schrödinger system. That is the first part of the statement. So, and to show that U bar and V bar are maximizers of the dual problem, I'm going to basically use the equivalence that 2 if and only if 1. So what I'm going to show is that the epsilon of U bar and U bar C epsilon is, what I'm going to show is that like U bar C epsilon is equal to V bar, U bar C epsilon is equal to V bar. So and what we do, we write the difference between the dual function applied to U bar C epsilon minus the epsilon U bar V bar. This is basically the limit by construction of my subsequence of NK when it goes to infinity of UNK and UNK C epsilon minus the epsilon. So I'm applying this epsilon transform. Let me write like this: do NK plus 1, NK plus 1. And here I have U and NK, V, NK. So in what we have, so this must be, this limit should be by force equals to 0, because like this is a sequence of bounded functions, so bounded by the primal problem, so it should have finite increments. So if I compute this difference, this should be equals to 0. Then we have that this quantity is equals to 0, but this is equal to this if and only if V bar is equal to U bar C epsilon. See, this is one of the properties that we show. That like when you apply the C epsilon transform, this quantity is always bigger or equal than this, and it's 0 if and only if V bar is equal to the C epsilon transform of 1. Okay, analogously, by changing U to V, so I do the same game, so now I take V bar and the V bar C epsilon transform, and I do exactly the same computation, we also get, analogously, we also get that U bar is the V bar C epsilon by arguing exactly in the same way. Okay, so this shows, if you all agree, this all show the first part of the theorem, that like we have a sequence AN, the sequence of synchron iterates AN converts to A, the sequence BN converts to B, where A and B solves the Schrödinger system. And here, the only property that we're using here to show that U bar and V bar are maximizers. So this implies that like U bar and V bar are maximizers. And this is due the proposition 2 implies 1. And we know that A bar and V bar, A and B solves the Schrödinger system because 2 implies 3. Or 1 implies 3. Okay, so what remains to show is that gamma NK, that is given by this converges strongly in LP to gamma bar epsilon. But here we have everything. So this is fine because we know that, so I can always put a scalar and divide that I do not change the value of the gamma any k. So lambda n is basically the exponential of the little ln divided by epsilon. But like I omit here is just this because of the invariance of the dual problem by summing and subtracting a constant. So I can also sum and subtract a constant here, U bar plus A and V bar minus A, and this does not change the value of the dual problem. So, and this is true. So this is basically true because like A and B are converging to A and K, and B and K are converging to A and B. The cost C is bounded, so the exponential of C is Lipschitz, like on bounded domains. So you get this strong convergence in LP. So then, like, we have everything. So, and this, like, has you, just to stress again what Andrea says, is like, this is like really a proof using compactness. So we say that there exists a subsequence that converges to the solution of the optimal transport problem, but we don't know any property of the system, of this sequence. We don't know how fast this sequence converge. And like, to understand it, we need to do a completely different computation. We need to do a completely different approach. Okay? So questions, is it clear, the proof? Let me see if I want to say something else. So, okay, regardless of the data, so for any rho 1 and rho 2, here we are using a technical hypothesis that the cost function is bounded. So under the assumptions that the cost function is bounded, we can guarantee that for any rho 1 and rho 2, the synchron algorithm converges. So here we are showing the convergence in LP, the strong convergence in LP, because we are using the property of the C epsilon transform. But for example, if you assume that the cost function is Lipschitz, you can get in the same way that like your C epsilon transformers are Lipschitz, and you can extract a convergent subsequence by using Arzela-Ascoli and do a similar result. So, and you get the convergence for Lipschitz functions. Good. Very good. Okay, so let me do this. To be very complete, let me prove the proposition, which I think that is very nice because like the proposition, you are going to basically use a lot of things that we learn on the way. And it's a way of like practicing a little bit all the results that Simone and I presented to you. So if you go to the literature, in particular, like to some reference that I presented in the first lecture, you see like that there are many different proofs of the convergence of synchron algorithm. some of them more geometrical, but like this one, like is one possible proof in for the entropic regularization, which has more like a calculus of variation taste. Other proofs that are based like on fixed point methods, like has the advantage that gives you like some information about the rate of convergence. So the disadvantage of this one is that like to get the rate of convergence, you need to do a part computation. Okay? So if there is no questions, I go to the proof of the proposition. Good, so let's do the proof. Proof idea. And here you have the proposition. So the way that we are going to proceed is like we are going to prove that 1 implies 2, that implies 3, that implies 4, and that implies 1. And then we prove it. So let's see if we can do this. So the first one, let's show that like 1 implies 2. So what we have is U star and V star are maximizers of the dual problem. That is what we have. So and we know that if we apply the C epsilon transform, let's say in U star, by a property of the C epsilon transform, we increase the value of the dual problem. So this quantity is going to be equal or equal of this one. But like by using the hypothesis of that U star and V star are maximizers of the dual problem, we also have that U star V star is bigger or equal than the epsilon U star C epsilon. But like what we basically do, so this is by hypothesis. And this is like a property of C epsilon transform. So basically what we show is the equality, but like those quantities are equal if and only if V star is then the C epsilon transform of U star. Then we prove that V star is the C epsilon transform of U star. I just do the same computation exchanging U star to V star. Then I prove also the second part that like U star is the C epsilon transform of V star. All agree? So maybe I do 2 implies 3 because I'm a... So now let's do that the 2 implies 3. So I assume that the property 2 holds, and I want to show that pi star defined in this way is a coupling between rho 1 and rho 2. So what does it mean being a coupling of rho 1 and rho 2? So I want to compute, for example, pi star, so the first marginal, let's say with respect to rho 1 of x. So this is exponential of U star of x plus V star of y minus C x and y divided by epsilon d rho 1 of x. And here I use the hypothesis. So I use the hypothesis that since I'm integrating x, so I'm going to use the hypothesis that V star of y is the C epsilon transform of, so let me use the hypothesis here. So I'm using here the hypothesis, so that V star of y is like minus epsilon log of exponential of u star minus c divided by epsilon with respect to the rho 1. So, and basically what I do is this is equal to, I can put d star epsilon outside, then I integrate exponential of this guy here. But since v star is precisely given by this, so this basically implies that we have it. So this quantity is basically equals to 1. So in this, I'm showing that, like, if I take the marginal in rho 1, this is precisely equals to 1. And similarly, if I do the integral of pi star epsilon x and y with respect to rho 2, we can also show that this is 1. Everything's okay? So we did 1, 2, 2, 3. Now let's do that 3 implies 4. So what we know, so let's call like c epsilon gamma, the integral of c with respect to the gamma, plus epsilon in the entropic term. So this is like the functional that we defined in the primal problem. So this d rho 1 and rho 2. So we know that that is what we also wrote as like epsilon, the Kiel divergence of gamma with respect to this exponential of minus c divided by epsilon. So we know that this entropic cost function is bigger or equal than the epsilon of u and v for all epsilon. And we also know that, like, if you take the optimal one, if you take the pi star, this is gonna also hold true. So this holds for every gamma. In particular, this holds also like for the optimal one. Let's see. So probably this. Let me check so I don't do a huge tour. Okay, so what I'm saying is like this holds true for every gamma in pi of rho 1 and rho 2. So what I want is this. This is true. So if this holds for every gamma and every u and v, this also holds for u star and v star. So this holds for every gamma that is a coupling between rho 1 and rho 2. These ones, since I'm fixing now gamma star, this holds for every u and v potentials. So in LEXP. And since, so now by hypothesis, we have that gamma star is equal by exponential of u star v star minus c divided by epsilon. So we can verify that actually we have the equality. So this, I'm not going to do the computations, but like we can verify that like the equality actually holds. So now let's use those three inequalities and see what we get. So if you use this, so like here we have, so let's write the first one. So the first one tells that KL of gamma is less or equal than the epsilon U star V star plus epsilon, but this quantity is precisely this one. So this in particular tells me that like pi star is the optimal for the KL of gamma, so for the primal problem, because like pi star is always smaller or equal than any other gamma. And we also know by the last formula that this is equal to. So basically this implies that OT epsilon, so if I take the minimum here, is equal to D star, U star, V star, plus epsilon. So and then we prove that 3 implies 4. So to finish the circle, we do that 4 implies 1. So and to do that 4 implies 1, so we know that always, we have used this a couple of times, the primal problem bounds the dual problem from above. So the primal problem is always bounded from above of the dual problem. But like by hypothesis, we have that the following equality holds. So by using those two things, so I have this equality, this inequality, and this equality, we just get that the epsilon of U star V star is bigger or equal than the epsilon of U and V. So if these U and V potentials, if the first inequality holds for every U and V potentials, so we have that the epsilon of U star V star is always bigger than the epsilon of U and V for every U and V potentials. Which basically is saying that U and V are optimal potentials of the dual problem. See, I like a lot this proposition because like it's a very simple manipulations, but like we needed to use everything that we prove in the first lecture. So it's a very nice exercise to use those tools. And this completely characterizes the primal and dual relation. So that was our philosophy. So we start with the dual problem. We obtain some a priori estimates to get existence of the maximizers of the dual potential. And this proposition basically tells us like by doing those equivalents, we get a completely characterization between of the primal problem. So, Andrea, you are looking to me. Do you have a question? So is the last one, so we can do a lot of philosophy here.
Yeah, maybe you have already told it the other day, so but I don't remember, so we'll ask again. I was wondering, you said you came up with this formulation, your formulation because it is natural in some situation, because it is better for the computation. But I was wondering, how do you come up with exactly this formulation? Let's say you try some formulation and you say that this was better than other, or do you rely on some other works? How you came up with your terms of regularization? Don't know if I express myself.
No, let
in
me
a good
see.
way.
Let me see. So the question is, let me see if I understand it. The question is, why we added entropic regularization
why
and
that?
not any
Yeah.
other entropic
Yeah,
any other regularization?
Why that one?
Okay, so why that one? I guess this I can give you an answer in 30 seconds. Because we love the property of the exponentials. So when you have the entropic regularization, to be very precise, the channel entropy, that is like gamma log gamma, what we get is that the solution of the primal problem is given by A times B times exponential of minus C divided by epsilon. Now that you see the proof, you know that A, B are basically exponential of U plus A is exponential of U and B is exponential of V. So basically, this is very nice because we use the property of the exponential, that the exponential of the sum is the product of the exponential. So you can decompose A and B in that way. So, and we like this a lot because we know that our solution is a Gibbs energy, so exponential of minus C divided by epsilon, but we need to find those weights A and B in a suitable way, such that the functions A and B grants that pi epsilon has the nice marginals. And this A and B is super cool because, like, if I integrate with respect to the row 1, that is a function of x, I can put B outside, and I write this system. If I write B, and I do this as well, what is the pain if I do a different type of regularization? No? What is the pain is that, so in the general case, so this is not anymore the entropic regularization. So imagine that now I regularize with a function phi of a gamma with respect to the row. I need to have some nice properties of this phi, but like, let's say this phi is convex, is proper, has like linear growth at infinity, so has nice properties here. For example, the channel entropy is one of them, but I could take it like the quadratic or the power p. What we can show is that like the gamma epsilon, and now I stress that is for this specific phi, is given by the derivative of the Legendre transform of this beast, where U star and V star are going to be the corresponding maximizers of the dual problem for this specific entropic regularization. And what is the pain? Think about the simplest case, the quadratic. The Legendre transform is the quadratic. Take the derivative, very nice, take out the power, so I take the positive part of this one. So take the positive part of this one, even if it's like the easiest regularization, I cannot play this game anymore. Or I cannot play this game necessarily like for any other entropy because I do not have this. I cannot take U outside when I integrate in the row 2. So then like I have some algebraic problems to write synchron as we like, using this system, using the Schrödinger system. But of course, you can tell me, but Augusto, you just show me this proof of convergence of the synchron. And this proof basically tells you that like it's very natural to look at the synchron algorithm, not has a matrix scaling where I update A and B, but is extremely natural to look at synchron, has like a block coordinate ascent of the dual problem. And I say, problem solved, use this entropic regularization. Instead of implementing synchron in the way that we implemented during the practical section, now look to the dual problem for any kind of entropy regularization for any phi. So, like, at least provided that you can compute analytically the Legendre transform of this phi and implement the synchron algorithm has like a block gradient ascent. Very fine. So that is the stuff that like you fix. So you have a D, you have a function D epsilon with the entropy phi. So you fix V and you maximize in U. Then you get U bar that you maximize it. Then you use this U bar, but fixed it and maximize V. So it's gradient ascent, but like in each one of the variables. So you see, like, so then like you can, if you take a general entropy, you cannot anymore think about synchron as like this system, but you really need to approach the problem like in our proof. So you need to look to the dual problem, this like block gradient ascent or stochastic method that you update U and V at the same time. So then you choose, but you really need to look to the dual problem. So, and that is one of the reasons that, again, I can speak for you as well, that Simone and I, we like a lot this kind of calculus of variation proof, because like this kind of techniques can be generalized like in different contexts, in particular when you have general entropy, or even when you have like a finitely many marginals. So instead of computing just the entropic regularization between rho 1 and rho 2, imagine now that you want to find a coupling of finitely many probability distributions. And this I maybe can give an example in a second. This answer, it was not 30 seconds, but like this answer your question. This is the very nice, so good. Okay.
So if we change phi, is there a hope that maybe for a special phi you have rate of convergence, or like no, you have to do?
Like as far as I know, the rate of convergence that I know are for the channel entropy,
Okay.
but there is hope that you can do in general.
Okay.
But this is not published because the people who are working on it are very keep the computations by themselves. So I cannot say you go to archive and you are going to find it. Do you want to comment anything?
No, but it's true that the proofs that are available, I think they work also in the general case. Also the quantitative convergence. The problem is that the up to now the quantitative estimate of convergence, at least for the linear case, so the really exponential minus something n, this something is like super ugly. It's like e to the minus e to the L infinity norm of c divided by epsilon. And so since you have a to the something divided by epsilon, as long as epsilon is like 0.1 or 0.01, it means that it takes like more than the age of the universe to converge. But this means that the proof is not optimal, because we see that there is convergence, which is very fast. So.
Okay, this answers your question. Very good. Any other questions? Let me use the 15 last minutes to try to do something crazy. So just this is a comment that is not very crazy, but like, let's discuss a little bit about the role of reference measure, because like when I define the entropic regularization of optimal transport, I say, listen, our data, we have rho 1 and rho 2. Those are like the measures that we have. Why not define the entropy as like the relative entropy of the coupling gamma with respect to the tensor product of rho 1 and rho 2? Because I don't have any other measure to work with. So if we are, for example, in RD, we have a very nice reference measure to work. We have the Lebesgue measure. So why not define the entropic regularization of optimal transport by simply taking the minimum of pi of rho 1 and rho 2 of the gamma, CD gamma, and now here I have the gamma log gamma dx and dy. And I assume that like rho 1 and rho 2 are absolutely continuous with respect to the Lebesgue measure. So here I have R to D and R to D. So what can we do? So this like does not make any difference for this type of entropic regularization. So when we use the channel entropy, and like the computation is pretty simple. So let's write the Radon-Nikodym derivative of gamma with respect to rho 1 and rho 2. So this is a function of dx dy. So let me see what is the direction that I want to go. No, I want to do the opposite. So I want to write this as the Radon-Nikodym derivative of the Lebesgue measure in the product. So it's precisely the Aragon-Decoding derivative with respect to the product measure. Then I take the Aragon-Decoding derivative of rho 1 with respect to the Lebesgue measure in D times the Aragon-Decoding derivative with respect to rho 2 with respect to the Lebesgue measure in dimension D, because my space is RD. So now let's compute the entropy. So let's compute the entropy with respect to the x dy. So this is basically log of gamma with respect to the Lebesgue measure, d gamma. But like by using this relation, we have that this is basically equal to log of d gamma, the product measure, with respect to the product of rho 1 and rho 2, times rho 1 divided by Lebesgue measure, and rho 2 divided by the Lebesgue measure. This everything integrated to rho gamma. But like now using the property of the log, we have that this is basically equal to the log of the gamma with respect to the product in d gamma. So now I look this as the relative entropy of gamma with respect to the tensor product of rho 1 and rho 2. We have a log of the rho 1 d gamma plus the log of the Aragon-Decoding derivative of rho 2 with respect to the Lebesgue measure. But what we are doing, so we are minimizing among all the couplings gamma that are couplings between rho 1 and rho 2. So, and if I use that gamma is a coupling between rho 1 and rho 2, so here I have d gamma on x and y, but this is a function that depends only on x. So this guy is basically integral of rho 1 log rho 1 dx. And here the same. So this is a function of x and y, but I'm taking the log of a function that only depends on y. This is precisely the Kullback-Leibler of rho 1 with respect to the Lebesgue measure in D. And here I have the same. This is the Kullback-Leibler of rho 2 with respect to the Lebesgue measure in D. So basically, when I'm minimizing gamma, what I get is that the entropic regularization with respect to the Lebesgue measure is precisely, let's say, the cost plus epsilon, the entropic regularization with respect to the product space, rho 1 and rho 2, plus a constant. So this guy depends only on rho 1 and rho 2, but does not depend on gamma. So the value of the minimum is different, but the argmin is precisely the same by just doing like the change of coordinates, by just taking the gamma with the right density. So what we just show is that like the mean is like the minimum with the Lebesgue measure, that is this one. So let me write this in the correct way. So this is exactly the integral of cost plus our favorite one, that now I'm taking the entropic regularization with the relative entropy with respect to the product. But this means that this is equal to this minus those two terms. And this I'm going to stress that I can take this out of the integral. Rho 1 with respect to the Lebesgue measure minus KL rho 2 with respect to the Lebesgue measure. And here I put epsilon, and here I put epsilon. So basically, this is just a constant when I'm minimizing. So actually, it does not make any difference if you change your reference measures. So, and if you can think a little bit, and you can see that in this case, the Schrödinger system means simply when you have the Lebesgue Lebesgue measure. In the Lebesgue measure case, you have basically like the optimal gamma epsilon. You integrate in dy. This gives you rho 1 of x. You integrate in dx. This gives you rho 2 of y. We still have that like the optimal solution is given by exponential of u plus v minus c divided by epsilon. But here we are thinking that this is a density with respect to the Lebesgue measure. And the only difference is when you write this guy using the expression in terms of the C epsilon transform, you are going to get a C epsilon transform tilde of u that is basically given by log of exponential, log of the integral of exponential of u of x minus c in dx, because now the reference measure is x, but then you need to add a constant that is like rho 1, rho 2 of y. That is basically, if you put here inside, you get precisely the second, the C epsilon transform that we introduce. So like in the end of the day, the synchronous iterates are exactly the same up to a change of variable. So then the kind of results that you can obtain is that like the potential u tilde minus epsilon log of rho 2 is bounded in L infinity as long as C is a bounded coast. The same for V. So V tilde minus epsilon log of rho 1 is bounded in L infinity as long as C is bounded, and then we can do the same analysis. So we needed to put some extra hypothesis that like rho 2 does not vanish in sets. So it's always non-negative. So it's always strictly positive. So the log is well defined. But let's say the analysis goes in the same way. Okay? This is just a technical remark, but not to finish with a technical remark. So maybe I needed to move to the slides. Let me just say what we would love to present if we have the 5 more hours of this thing. So let me do something very dangerous. Try to log in on Zoom in public. So just to say what we can do with this. So Simone proved today that like the WP is a distance on the space of probability distributions with finite p moments. So one very natural way of using this kind of tools is, imagine that I have a data that can be expressed as probability distributions, and I want to do some sort of density estimation. Imagine that I have rho 1, that is my data, and I want to somehow finding what is like the closest probability distribution that belongs to a class, that this class could be probability in X, or could be a parametric class that approximates this distribution. So imagine, for example, instead of taking nu that belongs to P of X, imagine that nu is parameterized by theta, where you are trying to find the best nu in this class theta. So the easiest way, thinking that you are in 1D, so you want to approximate your distribution rho 1 using Gaussians. So Gaussians in 1D are completely characterized by the mean and the standard deviation. So your theta is basically the mean and standard deviation. So you want to fit the best mean and the standard deviation among the Gaussians that fits your data. So when you have the choice, you can choose to do this using the entropic regularization, because we know how to compute using synchron algorithm, or theoretically, you can also say, I want to compute this using the p versus the distance. Because in the first day, we saw some examples where it makes much more sense to compare my data using optimal transport distance rather than use the Kullback-Leibler divergence, or rather than using the Euclidean distance. Because, for example, if my data and my parametric class has disjoint support, in those cases, my Kullback-Leibler can be plus infinity, or my Euclidean distance can say that the data is very far apart. For example, in those pedagogical examples. So in here, to do this under a parametric class, so one of the things that we need to do, so we want to find a minimum of a function that depends on rho, we needed to know somehow how to compute the variation of the function OT epsilon with respect to rho. So I want to take the derivative and put equals to 0 to find the critical points. So we can do this. So one, we can show that OT epsilon is a continuous function. So we have continuity with respect to the data, with respect to rho 1 and rho 2. This is like continuous on the weak star convergence. So this tells two things. So this tells one, that the Sinkhorn algorithm is robust. So if I perturb a little bit my data, the Sinkhorn algorithm is converging to something that is very closer to the non-perturbed data. So this is precisely the continuity. And also the continuity tells me that, like, okay, this function is continuous. And I can also compute the Fréchet differential of OT epsilon. So actually, if you are in the same setting that we are, so suppose that nu and mu are probability measures. So the Fréchet differential of OT epsilon is given basically by the Kantorovich potentials. So, and you know how to compute the Kantorovich potentials using the Sinkhorn algorithm. So in the practical section, we always plot gamma star epsilon. But you know that gamma star epsilon is the exponential of Kantorovich potentials minus cost divided by epsilon. Take the log, you can return or not even that, like when you do the Sinkhorn algorithms, you are basically computing the potentials and then you return the gamma. So you know how to compute V star and V star. So that's why the dual problem is very important, because when you are computing like the Fréchet differential, for example, to do density estimations, they pop in very clearly. So this is the first thing. So, or you can think more generally. Imagine that you want to do linear regression, but now that you learn that there exists a very fancy distance and a very fancy geometry to do linear regression, why not now consider finitely many probability distributions in X, so now in the same space, and now you compute like a weighted average. So if you take lambda 1, basically 1 over n, what you are computing is basically the mean. But now you are computing the mean, not in Euclidean spaces, but you are computing the mean in the metric space of, it could be like the WP. So then we are really doing the mean using the Wasserstein space, or if you use the entropic regularization, you're computing like the entropic regularized mean. And here you have the same kind of thing. So to find the best mu, you need to compute like the Fréchet differential of this guy. This is going to give you a function in terms of the Kantorovich potentials. And just to give a feeling how this is meaningful, so in a paper of some OT researchers with people that works in the Pixar, they try to use this kind of geometry of Wasserstein spaces to make interpolations between shapes that they can do, for example, in cartoons. So suppose that like your measures rho 1, rho 2, and rho 3 are like the uniform distribution in the donut, the uniform distribution of this shape of a pig, and the uniform distribution of the shape of a duck. So those are 3 probability distributions. And now I know how to compute the optimal transport between those 3 shapes. I can write the geodesics, or at least the approximated geodesics if I use the entropic regularization of optimal transport like Simone showed today. So and now by choosing lambda 1, lambda 2, and lambda 3, different values of lambda 1, lambda 2, lambda 3, such that they sums to 1, I can compute like the intermediate states of those shapes. Yes.
But so what you're showing here in the figure is precisely the minimizer of this, right? So
I'm doing the arg
mean.
Yes.
Okay.
Like it's a little bit more complicated. So I'm taking like the arg mean of the row.
Of the nu?
The nu, exactly.
Okay.
So the nu, I don't, so the arg mean of the nu.
Okay.
And what I'm, for different values of lambda 1, lambda 2, lambda 3, you know, what I'm putting here is like is the support of this guy for different values.
So the lambdas span the triangle somehow, and the solution is the interpolation. Okay.
Exactly. Okay. So for example, this one, I'm taking, let's say, lambda 3 equals to 0, and I'm just doing interpolation lambda 1, lambda 2, is exactly what Simone did. Here, the same, I take another one, lambda 1, let's say, to 0, And here I put lambda 2 to 0. And in the middle, I have those guys.
And they're using the Wasserstein as the
They are using, if I do not mistake, the entropic regularization.
entropic
Yes,
realization with the
if I do not mistake.
with the square cost.
With the square cost.
Okay, cool, very cool.
And that's why it's because it's cool. You see, like if you look to the metric I, like if you look like to the metric I, makes a lot of sense this kind of geometry on the space of shapes. Like I convinced you in the first lecture, like if you look to histogram of images, Wasserstein is very natural to use. But you see, in the I's metric is a very pleasant distance. But of course, the big pain is that like when you have the Kubat library, you plug your data, let's say mu and rho, and this gives you a number. When you have the optimal transport problem, you need to solve a variational problem. So you need to compute this numerically. So although you get like a very pleasant result for the I's metric, you need to pay a computational cost. So the numerics. And like we, as a mathematician, like, did I answer your question?
Yeah. Thank you.
Okay. So like another draw point is that like we as mathematicians, we love this type of results of convergence of synchron when the number k of iterations goes to infinity. But like in practice, as you did in the practical section, we choose a stopping time. So k never goes to infinity. So okay, the number of iterations never goes to infinity. K is a number that is fixed. Yes, go on.
Thank you. I was wondering, seeing the picture, this work, if let's say the shape has the same dimension, let's say you can transform a segment into a square. I think I was wondering.
You can do so. This is like probably this is if we have more 10 hours of lectures. Like we can do also optimal transport with different dimensions using like different formulations of optimal transport. You need to choose your cost function, or you need to do an analysis a little bit more careful and understand like the support of the. But yes, you can do things on the same dimension in different dimensions, but the machinery goes a little bit out of the scope of what we show here.
Okay,
but you cannot apply directly this.
Okay.
This I agree.
Okay, thank you.
Okay. So, and just to conclude, so we like a lot to prove the convergence of synchron. So we like a lot this kind of very rigorous mathematical results that like we say, okay, when the number of iterations k goes to infinity, we are converging to the maximizers of the dual problem. And with the maximizers of the dual problem, I know how the primal problem works. Because like when you are doing, I don't know, statistical machine learning applications, we want to exploit like the mathematical properties of the potential, the continuity of my OT epsilon, so the continuity of the Wasserstein distance to prove, to understand a little bit the theory behind the algorithm that we are doing. But like the big challenges here are two. One is what Simone commented in this morning, is that like in general, when we compute this numerically, we never compute for nu and rho 1. We always compute to the empirical measure of mu and rho 1. So we are doing like you are taking like a sample of those guys and performing the numerical computations. And when I take the sample of these guys, so I look to nu and u, only the empirical distributions, I'm making a statistical error. So the statistical error that Simone says that like in the worst case scenario, when I compute the difference of this guy with the Wasserstein distance and their empirical counterpart, so the dependency n like grows like n at -1/d. So you have the curse of dimensionality. So like you need an exponential amount of points n on the support of the distributions to be able to break the curse of dimensionality. So there is one imprecision that we get by this, at least in the worst case scenario. And the second one is, we know by the proof that we did today that like when k goes to infinity, the synchron iterates are converging to the maximizers of the dual problem. But when k is fixed and is finite, this is not true. When k is finite and finite, we are basically approximating the empirical marginals of mu and u up to a certain precision that could be also like the machine precision. So they are not actually the control. And this is also another source of error that is not statistical, like the sample estimation that Simone did this morning, but is more of order of the optimization, is more of the order computational. So like we have to deal in practice, although the theory is beautiful and works very well on the blackboard, we needed to deal with also a computational error and a statistical error. So it would be very nice to do the second part of the course where we exploit all those things together. But I hope you enjoy, like we try to do a self-contained presentation with like some details, and hope that this can inspire you to go a little bit more deep on the topic. Okay, so I hope that we are not half past midday, but I would finish here. Thank you, guys.
Okay, so thank you very much, Augusto, for
Thank
finishing
you
this,
for the
optimal. Yeah. So do you have other questions, comments for? Yes.
So does this OT epsilon define a distance also, or
no? For example, so one way to say that this is not a distance is that if you take OT epsilon of nu and nu, this is not equal to 0 because of the entropy. So even C is a distance.
Yeah.
So, and this is a sort of bias, right? So this introduces some bias. You can adapt this, you can solve this problem by like consider a sort of a divergence where you take this guy minus terms that take out this bias. So what are these terms? Minus 1/2 OT of epsilon of mu minus 1/2 OT epsilon of rho. So then you can eliminate the bias and you have this, but then you get a divergence. You don't get a distance.
Okay.
So, but anyway, divergence are also good as loss functions, and you can live with that.
Yeah. Okay. Thank you.
Called synchron divergence is
the name.
Yeah.
So I want to see if I understand. The way that in which I can solve this problem is using the slide before. So I extract the functional derivative, I put this to 0, and I obtain the nu that minimizes it, right?
Yes.
Okay.
And like the only thing that we need to show here, and is a little bit under the carpet, is that like the solution is basically like the average using the different transport maps between those distributions. So like you basically do the average and you take the push forward of the solution pi star, and then you can compute those interpolations. So like you need in the end of the day, like computing an average using the Wasserstein geometry, and you need to do basically like the equation of the geodesics, but with multi-marginal, you need to do like an average of the different optimal transport maps. So there is a lot of stuff under the carpet here, but like we needed to think a little bit, and I'm very happy to discuss how is the precisely implementation of this. I want to finish with a nice picture, not with like bad news.
Okay, so we resume this afternoon with the last lecture. So Professor Villa, please.
Thank you. So this afternoon, I will continue a bit what we started in the last lecture. So the idea is to treat non-smooth cases, non-smooth minimization problems, and in particular, we will I will introduce a new method to minimize functions like this. So maybe I put a title. So it's structured non-smooth optimization. And as I was saying in the introduction, both the machine learning world, but also the inverse problems world, motivated the study of function having this structure, so a sum structure. And because oftentimes you have a data term plus a regularization. So this is a structure that appears very often. And the assumptions are that this function is differentiable with a Lipschitz continuous gradient, And this one instead is just convex. So both of the two are convex. One is differentiable, the other one is just convex and lower semi-continuous. So the method that I will introduce today is tailored for this specific case. In order to introduce this method, I need a tool, which is the key tool of this, is the, yes, I don't know, the key tool for this lecture again, and is the proximity operator of F. So in this case of G. Or proximal mapping. That maybe here in PISA you call differently. I don't know. We will maybe you will tell me. So this is the. So for us, this definition was given by this object was introduced by Moreau in the 60s. I think 62, and maybe there is another paper a bit later. And the idea is this. So you have a function, which is just, let's call it G. So let G be convex, lower semi-continuous, and proper. So plus infinity as a value is okay. And then you define for every gamma bigger than 0, you define this function, which goes from H to H, and is defined as follows. Prox gamma G of X is the minimizer, so I write argmin, of the following sum. And the argmin is over Y. So basically what you do in order to compute this proximity operator of the point X, you take your function G, and then you regularize it with a quadratic term which is centered at X. Okay, so you do a Tikhonov of regularization, let's say, and you minimize this sum. So of course this will depend on gamma, and that's the definition. Okay, just two comments. First, when I minimize this sum, automatically I should go in the, so the minimizer will be in the effective domain of G. So in the points where will be a point where G is finite. And the second comment is that this, let's say this equality is well posed in the sense that here I have a strongly convex function because I add this strongly convex term to a convex function. So this is strongly convex. And therefore, this minimizer exists and it's unique. So this is well defined. And so this is, okay. What I wanted to say is that this is in the domain of G. Okay. Then, yes, then we can say something more and try to characterize in terms of first order conditions this proximity operator, this proximal point. So this point is often called the proximal point of the point X. The difference between proximity operator and proximal mapping is due to the two schools. So in France, you call it proximity operator, and in the US, you call it proximal mapping, basically. And so if I write the first order conditions to express the fact that the prox is the minimizer of that function, what I get is that 0 should be in the subdifferential of G plus 1 over 2 gamma x minus dot square evaluated at the prox. So let's call this P. And then, so what I have to notice is the fact that here I have a sum, I should take the subdifferential. This is a differentiable term, so it's in particular is defined. Its domain is the whole space. So the qualification condition is satisfied. I have that the interior of the domain of this function intersects the domain of G, and so I can apply the sum rule. And this gives me that 0 belongs to the subdifferential of G at the prox plus the derivative of this, which is 1 over gamma y minus x. Sorry, p minus x. Okay, and so from here I derive that x minus p over gamma belongs to the subdifferential of G in P. So this is the first order characterization of the prox. So I know that this difference will be in the subdifferential at the point P. This gives also the occasion to write this, the definition of the prox in a slightly different way, which is the most suitable for generalizations to more general operators rather than the subdifferential. So here what we can say is that this is again in other ways equivalent to the fact that x belongs to P plus gamma, the subdifferential of G at P. Okay, and this can be written as x belongs to identity plus gamma, the subdifferential of G at the point P. And so basically what we have seen here, the fact that this inclusion is satisfied if and only if P is a minimizer of this problem here, tells us that the inverse of this operator is single valued. And so this is equivalent to say that P is equal to the identity plus gamma, the subdifferential of G to the minus 1 evaluated at x. And this is a single valued. So this is really a mapping. And if you're familiar with the resolvent of a monotone operator, this is exactly the resolvent of the monotone operator subdifferential of G. So here you can put, instead of the subdifferential of G, a monotone operator, A. And this is the, let's say, one of the possible generalizations of all this stuff to deal, for instance, with saddle point problems instead of minimization problems. So what I say is tailored for the minimization. So with this definition, we can do an example, for instance, and compute the proximity operator of the absolute value, for instance. So, example of the absolute value. And I would say this is the most important computation. This is the computation that justifies all these series of lectures, at least in the applications, in the sense that everything started in 2004, 2005 with this prox of the absolute value and then of the L1 norm. So this the absolute value is like this. We already computed the subdifferential. We know that the subdifferential, so if this is G, at x is equal to 1 if x is positive, minus 1, 1 if x is equal to 0, and minus 1 if x is negative. Then I will write, I want to draw, just to make it with a drawing, this map, identity plus gamma, the subdifferential, and then I will invert it graphically, let's say. So what I can do is that the subdifferential of this map can be represented like this. So it's minus 1, 1, and then I have 1, minus 1. So let's take gamma equal to 1. It's the same if gamma is positive, is different. So now what I have to do, I have to add the identities. What I get is that to this thing, I have here, it remains as it is, and here instead I have to add the identity. So this final red line is the graph of identity plus subdifferential of G. And now I have to invert it, and so I take the symmetric with respect to the 45 degrees line, and I get this thing, -1, 1, and then here, more or less, something like this. And this orange graph is the graph of the proximity operator of the absolute value. So this tells me more precisely that the prox of the absolute value at x is, so here, x minus 1 if x is bigger than 1, 0 if x belongs to -1, 1, and x plus 1 if x is smaller than -1. And this is called, this is a, let's say, famous, I would say famous operator. This is called soft thresholding of, this is the soft thresholding of parameter 1. And it's called soft thresholding because, as you can see, if you put a number and you compute this prox, you will threshold it if it's between -1 and 1. So if it's sufficiently small, when you apply this prox operator, you will threshold it and put it equal to 0. And instead, if it's bigger than 1 or smaller than -1, you will, let's say, decrease its absolute value. Okay, so it's a soft thresholding. It's different compared to the hard one, where here you would have a discontinuity, right? So if you would leave the vector unchanged. Yeah.
Is there a reason why we have fixed gamma to 1?
Ah, no. So it was just for to have one less parameter. So here, of course, you can put a gamma, and what you get is gamma, gamma.
Okay, makes it okay.
Just because I don't like computations and
okay.
I'm always wrong. So I try to simplify to the
thank you.
the maximum level. Okay. Yeah, and this is S gamma. And so yes, so it's a Lipschitz operation, one Lipschitz. Okay. So and this is the difference basically with respect to the hard thresholding. So we can generalize a bit this thing by recalling a result that I forgot to prove last time. I already used it once, so maybe I write it now that it's the second time that I use it. So if you have a function which has which is defined on a product space, and of x can be written as the sum of fi of xi, where each fi is defined on hi. And sorry, this is G. I'm using G. Okay. And then what you can prove quite easily is that the subdifferential of G at x is the product of the subdifferentials. Okay. And this property immediately, thanks to the characterization of the prox in terms of the subdifferential, gives you the separability of the prox. So if you have a prox, so if you have a function having this form, this implies that the prox of gamma g evaluated at x can be written component-wise as the prox of gamma g1 at x1 and prox gamma gn at xn. Okay. This is okay. So once I have this equality, immediately from the proximal point of the absolute value, I can derive the proximal point of the L1 norm. So coming back to the example, if I take g of x, which is the L1 norm of a vector, so x now is in Rd, then of course g of x has this structure, and in particular all the gi's are the same. So this is the sum of xi, and then I can compute the proximity operator component-wise, and it will coincide with the soft thresholding operation for each component. So when I put the L1 norm here, I will get soft thresholding gamma of x1, soft thresholding of xd. So maybe two things, I should say two things. One is that this is a closed form expression, and this is not for granted, this is not true in general. So in general, I cannot write something like this. And the second thing is that it's super cheap to be computed. So when it's computationally is zero effort. Okay, you have just to check if your component is bigger or smaller than gamma, and then you threshold or not. See?
So just to, what is the metric? The distance, the scalar product that you put on the product is the
it's the
sum.
Euclidean. So I do the sum, yes, of the scalar
Okay,
product.
okay,
yes.
Okay.
Yes,
Right.
yes. So on Rd is the usual Euclidean scalar product in Rd. Yes. So the norm is the square root of the sum of the squares. Yes. No, sorry. Sorry. So this is g of x, and instead this is prox gamma g of x. Okay. Yes. Yes. Yes, exactly. So if you put that when you do the square norm, this is separable. So you get here really when you if you write the definition of the prox, you get a sum of functions which depend each one on one variable, right? Yes. Oh, sorry.
Sorry, is it a so basically, if I understand correctly, like these operators somehow clips the gradient to zero in a region which is far up to gamma from the non-differentiable point, and this is what we exploit for the computations. Is it right, this picture, or is it just a special case?
I don't know what you mean by the gradient, because I'm not. So what I clip here is just something that I can do on every vector. So I don't need the gradient, right?
Oh yeah, but like I mean the thing, I don't know if I'm picturing this right, but the thing is I would like to do somehow gradient descent on a function which is almost like that. So I have 1 or -1, but I have lots of problems around 0, of course. So in order to, instead of doing that, I set to 0 the gradient around the point.
So maybe yes, and maybe you are even I mean already. Yes, so maybe I write it. I don't know if I understood correctly the question. I'm not completely sure. What is true is that in principle, so there are two things that I should say. So I can define an algorithm, okay?
Okay.
And so it's never used. It's just a conceptual algorithm, proximal point algorithm.
Okay.
So this is Martinet-Rockefeller. So it was introduced indeed by Martinet and then popularized by Rockefeller. And I think it's 76. And what you do is this one. So you start from like 0, arbitrary, and then you do this. So indeed, this can be seen as a sort of replacement. So these algorithms converge. converge, and fantastically for every gamma bigger than 0. So you can choose gamma as big as you want. Okay?
I would have done it a different way, but I think of course I'm wrong. I would have done like xk plus prox plus epsilon prox gamma f xk. So treat this as a
yeah. And now if you want, yes, right. So I can say something more in the sense that what you can say about this. So it converges very well, very good properties for any gamma 0 function. So you don't need the subdifferential everywhere. You don't need to have full domain. So it's much better rather than the subgradient method. You have a convergence rate. If you want here, you can put a gamma k, which is given by, now I don't remember the constants, but usually are the same. So constant divided sum of gamma k. So this is on assuming that the minimizer exists.
Yeah. Oh, okay.
So you see that you can choose, in principle, if you choose gamma is big, going to plus infinity, you get very good convergence results, super good. The problem is that if you know how to compute the proxy in closed form, very often, I mean, you know how to minimize that. So this is not very useful. In which sense these converge? Because you can interpret it is very similar to the gradient descent method, and because both of them can be seen as discretization of the gradient flow, or in this case, the subgradient.
Okay.
So if you write, I came back to F, I'm sorry. So I will keep F now, because otherwise I will keep doing this. And so here it depends what you do, right? You can write xk plus 1 minus xk divided by gamma, let's say, in the subdifferential of f at xk, so is equal to a vector in the subdifferential. So here this means that xk plus 1 minus xk divided by gamma is equal to minus uk in the minus the subdifferential of xk. And here what do I get? I get that xk plus 1 is equal to xk minus gamma uk.
Yeah, exactly.
Okay. Now I do another thing. I discretize implicitly the equation, and I compute the subgradient, the subdifferential instead. I put xk plus 1 instead of xk. So I do an implicit discretization. And what I get is that xk plus 1 minus xk over gamma belongs to minus the subdifferential of f at xk plus 1. And therefore, I can write xk plus 1 minus xk in minus gamma, the subdifferential of g of f at xk plus 1. And here, if you put this on this side, you see that xk plus 1 is exactly equal to the prox. This implies.
Okay.
So in a sense, the two algorithms are different discretizations of the same evolution equation. If you want, there is another interpretation that makes this algorithm similar to the gradient. You can so now, okay. So you can take, if you have a gamma 0 function, you can consider its Moreau-Yoshida regularization. So you take the inf convolution with the square norm. So it's this one. So let me see. So it's F. So it's exactly the one defining the prox, but you see it, let's say, in the function. So, and it's even a minimum, so I can put in. Oh, it's the same. Okay. So f of y plus 1 over 2 gamma x minus y square. So if you consider this function, you can interpret this function as a regularization of your original function. So this is called, you do the if convolution between your original function and the square norm term. So you get something which is differentiable, and its gradient, so the gradient of f gamma, at the point X is not completely 100% sure on the formula, but is like identity minus gamma the prox.
Okay.
So in a sense, if you want, the prox is X minus gamma the subdifferential of this smoothing of the function. So you are doing, and you are still doing gradient descent, not on F, but on a smoothing of F.
Okay, okay.
So in these two senses can be seen as an approximation or akin to gradient descent.
Perfect. Thank you very much.
You're welcome. Okay. So as I was saying, when you ask the question, if you write the proximal point algorithm, this is really a conceptual algorithm in the sense that applied as it is not useful, in the sense that I will never apply the proximal algorithm to minimize a function, because in that case, I already know the minimizer, basically. And so instead, but in any case, this proximal algorithm is very useful. So, and the proximity operator is very useful when it's used in connection to structure. So when you apply it, let's say partially, not to the whole function, but just to, in this case, to a part, to a summand. And so this is what we will see later. Sorry, I should say one more thing maybe on the prox. So I think that so there has been a strong, I would say, a strong effort of the optimization community to compute proximity operators. So there has been years of work to find formulas to compute proximity operator of very strange regularization functions. I think now there is, if you check, I think Pesquet, Chouznou, so there is a web page containing all the proximity operators that are known in closed form, the ones that can be computed efficiently. So there is a sort of repository. So prox computation. But to be honest, I think that so really the most interesting, the reason why the prox became famous, at least is so well known and used, is the prox of L1 norm that you have seen before. And the other one, so I think I will not maybe compute it, is the prox of a norm. So, and this is used to solve, so very often you need to compute proximity operators of stuff like this. So you have L1 norm, which is the example, and the other example is so something like this. Either something like this, and this is the norm in the space H. Okay. So this is usually RD, if you want. So you have a linear operator, you apply it to X, and then you take the norm. Or different norms, in the sense that I'm thinking to total variation, for instance, that has this form. So you take a linear operator of a vector, and then you take a norm which is, I don't know, the sum of Euclidean norms. So it's a mixture between the L2 and the L1 norm. It's not, and which is so these kind of proximity operator are not available in closed form unless L is orthogonal. So you don't know how to compute it. You need an iterative procedure. Or, instead, if L is orthogonal, this can be computed, and the computation of this proxy is based on the so-called Moreau identity. So that's the other tool that I wanted to briefly introduce in order to close this very incomplete introduction to the proximity operators. So the other one is Moreau identity. So since Augusto is lazy and didn't introduce the Legendre transform, now, I don't know if you did it in the meanwhile. No. Okay. I was joking, so sorry. I didn't want to. Okay. So now I just introduced briefly the Legendre transform. So the Moreau, you have to take into account to I think, remember. So the way I like to introduce Moreau identity is the following. So basically what you have is that you can write this for every vector in H. So if you take V, which is a linear subspace, then you can write x as the projection onto V of x plus the projection on the orthogonal. Right. And the Moreau identity is a generalization of this equality. So it's the generalization of the idea that you can split the vector as the projection onto V plus the projection onto V orthogonal. So first thing to notice is that the projection is a proximity operator. So the proximity operator generalizes projections. So let's take, now I'll try to come back to G. So let's take the G equal to the indicator function of a closed and convex set. Non-empty. And then what you can see from the definition is that the prox gamma G of x is the argmin of the indicator function evaluated at y plus 1 over 2 gamma x minus y squared. And so this minimization is for y moving into h. Since here I have the indicator function in convex analysis is 0 on C plus infinity outside. So this means that you are minimizing this function in C. And so this is exactly the definition of projection. So the prox is a generalization of the projection. So here, and the second thing that I should notice is that, so I need this, I need to introduce this transform, which is the Legendre-Fenchel transform for us. So sometimes, more often like this, I have to say. So I will not say anything about this. Maybe Saverio will say something tomorrow. So the definition is this one. So you can define this for indeed for any proper f. I will define it just for an f for G for an f which is in gamma 0, and it's like this. So this is the definition. Okay.
Just a comment.
Yes.
So the comment is that actually we saw something like this morning, but very, very briefly.
Okay,
But it was just the soup of linear function is a convex function.
Exactly. So this is
without
the
proof.
function.
With the
Yes, me too. So I will not say anything. I will give just the definition. I'm sorry. So because if we start with this, so it's the starting of duality. So you can speak of this for many hours. But so this is a soup of convex functions, linear functions. Sorry, and so it's convex. This we know, and more generally, you can. So more specifically, I'll just write the properties that I need.
Sorry, is it just like the Legendre's form, like the one that?
Yeah.
Okay.
That's
perfect.
it.
That's it.
But I don't. So in the convex optimization, convex analysis books is called the Fenchel, usually transform conjugate, Fenchel conjugate to be more precise. I call it conjugate, but well, it's the same stuff. Okay. And so I just use it as a tool.
Thank you. Sorry, is there also a Legendre's transform with integrals somewhere?
I don't know. I didn't understand the question.
Is there a Legendre's form with integrals?
Is there?
Ah, the Laplace. Oh, no, sorry. My bad. Sorry.
So what you can prove is that if f is gamma 0, then f star is gamma 0, and the following properties hold, that are the ones that I want to that I need and I want to write. Theorem. So if you have f, did I write it? 0h, then you can prove is that 1. So this one we can also prove it. By definition, f star of u is bigger or equal than u of x minus f of x. So, and sorry, I wrote it like this, but it's not the right way. Usually it's written like this. So this is true by the definition. And then the point is that the pairs x, u, which satisfies equality are very, very special pairs. And this is the second point. So f of star u plus f of x is equal to ux if and only if u is in the subdifferential of f at x, or if and only if x is in the subdifferential of f star at u. And so here you see from this equivalence that as mappings, let's say as relations, the subdifferential of f star is the inverse of the subdifferential of f. Okay. With this, I can, so now that we wrote this, maybe one exercise that I leave as an exercise just to justify this introduction is the fact that when you do the Legendre-Penchel transform of the indicator of a linear subspace, what you get is the, sorry, here I should do like this. So the transfer of the indicator function of V, where this is linear, is a linear subspace, then you get exactly the indicator of the orthogonal. And so now I can rewrite this as the prox of the indicator function of the indicator function of V plus the prox of the indicator function of the orthogonal. And the Moreau identity is exactly the generalization of this formula to any, so sorry, here I should write, to any convex function f. Okay, so this is true. And what we write is this one. Do I have, yes. So the result is like this. So if I have f which is in gamma 0, then x is equal to prox f x plus prox f star x. This is super nice. If you add the gamma, is not so nice anymore, in the sense that here you have to compute the transform of gamma f star, and so you get gammas everywhere. Okay, so this is really the most nice expression. So the proof, we can write the proof because it's I think is easy and uses all the things that I already introduced. So I call this, okay, the prox, P is equal to the prox if and only if, so I canceled, I can write the first order characterization, so x minus P over gamma is in the subdifferential of f at P. Without the gamma, because it's 1. Thanks, Simone, for taking care of all this. And so here, what I should use is this one. So what I get is that P should be in the subdifferential of f star evaluated at x minus P. Okay. So now I want to write, let's say, add and subtract something in order to make this as this, so that I can interpret this as a prox. So this is equivalent to, let's say, x minus x minus p is in this differential over star at x minus p. So I add and subtract x, and what I get is this expression, meaning that x minus p is the prox of f star computed at x. So this means that x minus p is equal to the write it here. Okay, and this is the end, because then I take p on this side, and I have that x is the sum of the prox of f plus the prox of f star. So let's say the deep result is this one, which is the Young, also called the Young-Fenchel inequality, inequality and equality. Okay, and this is used. So this decomposition is often used to compute the proximity operators, in the sense that sometimes it's easier to compute the proximity operator of the conjugate rather than of the function f itself. And this is the case, for instance, for the norms, because you get that the conjugate is the indicator function of a ball, and so it's very easy to compute the projection. There is, I don't know, but you can compute the projection on the ball. At least you can write it. Okay. And especially this had an impact in the field of, so just to conclude, of sparsity-based regularization, where you have not just L1 norm, but maybe you have groups of variables that you know are interacting. So you want to put when you regular, I don't know if you know that L1 sparsifies, in a sense. All this story is okay for you, is familiar to you, or not, more or less. Because so for the L1 norm was used recently a lot, so in the last 20 years, because the idea is that maybe I just do a small, but very. So the idea is that you want to solve problems like this. So you have a linear system, and you want to find a solution which is the sparsest one. Sparsest means that as a small number of non-zero entries. So here we are in RD. This is usually called the zero norm, even if it's not a norm. And so there are a lot of results, I don't know, Candes, Tao, Romberg, that establish that this problem, under suitable assumptions on A, is equivalent to A. So this is to this. Why this is so interesting? Because this is a convex optimization problem, and we like it so much. We know how to solve it. It has a unique minimizer. This is a non-convex optimization problem, and it has been proved to be NPR, so computationally intractable. So then, this story is very nice, super nice. It's not really like this, in the sense that the conditions that you need to verify on A, at the end, verifying the conditions on A in order to have equivalence is as hard, more or less, as solving this. But at least you have you have classes of matrices for which you know that with high probability the condition will be satisfied, and so you solve this convex optimization problem. Okay, this is just the story in 30 seconds. So all this study motivated in the signal processing community, I would say, motivated compressed sensing community, motivated the study of problems like this, and in particular, where when you don't want to solve this system exactly because you have noise, you pass from this to something like this. Call it lambda. So you take the regularization and you have, let's say, the prototypical example of the structure that I was showing in the beginning. Differentiable function with Lipschitz continuous gradient plus non-smooth regularization. Okay, and this is called sparsity inducing. And it's used in many, many contexts, many more than this one. So even where you don't know what happens really, but you use L1 because it works in practice. And so this motivated a lot the development of algorithms which are tailored to solve this problem specifically. Okay. Yeah.
Thank you. Sorry, I lost myself in the last if and only if on the last proof because we have defined the proximity as an argmin and why it is equivalent to require that.
Okay. So you see here, if I move this x minus p on this side, I have that x is the identity plus the subdifferential over star evaluated at x minus p.
Okay.
So I can write this as identity plus subdifferential over star evaluated at x minus p, right?
Okay.
And now it means that x minus p is identity plus subdifferential over star to the minus 1 at x.
Okay.
But this is the definition of the
Yeah,
class.
it's okay.
Okay.
Thank you very much.
You're welcome. Okay, and so in this context, so I started and then I forgot why I started. So in this context, so L1 norm, let's say, is the basic, is the entry point. And then if you apply this kind of regularization to very practical problems that have been studied a lot by machine learning people and statisticians, where, for instance, this X is the, I don't know, the expression of a series of genes, then you know that there is a structure on these genes that if one gene is expressed, then other two must be expressed. So this, instead of computing this L1 norm, which induces sparsity, let's say blindly, without putting any relations between the variables, you like to use more structured functions where, for instance, you take the sum of Euclidean norms of subgroups of the vector. So if you have a long vector, I don't know, let's maybe, which is, we have 4 genes, we know that these two will be expressed together, two will be expressed together, and then instead of, let's say, and you want to induce sparsity, let's say you want a group to be 0, instead of using the L1 norm, maybe you use the sum of the Euclidean norm of these two vectors, okay? And these are called group lasso penalties. This is usually called the lasso. And instead here, if I take the sum of, I don't know, you can write it much more generally, I'm sorry. So, but I hope it's clear. So you have these joint groups, and then you take the Euclidean norm of these groups, and this is called group lasso, okay? To compute the proximity operator of things like that, you need this Moreau identity. So you can do the computations. You should do it. It's an exercise. And that's what motivated this kind of, again, results.
So we begin with the second part of the second to last lecture of Professor Villa.
Okay, so thanks. So the motivation for this second part, as I told you several times, is this one. So an algorithm, I have to say that an algorithm to solve this problem has been devised first by the inverse problem community, not by the optimizers, more or less at the same time, but the famous paper in the Dobeschi, De Vries, De Moll in 2004, and more or less 2004, 2005, there is a paper by Combet and Vash about the same, say, the generalization and the point of view I will explain now. Again, is 2004, 2005. Okay, so what is this algorithm? Is the algorithm that is called proximal gradient algorithm. So as I was saying, this algorithm will minimize a function which is like this, and with f, which is smooth, so the gradient of f is Lipschitz continuous, exists, and it's Lipschitz continuous. We take constant L. And then the other thing is that, okay, and the other assumption is that both f and g are convex. So per lower semi-continuous. And always standing assumptions, a minimizer exists. So there exists X star in argmin. Okay, so under these assumptions, what you can do is to, in order to derive the algorithm, is to write the first order conditions. So let's see what happens. I need to write 0. So we know that X star is a minimizer if and only if 0 is in the subdifferential. And again, I'm in the lucky case where since F is differentiable, the domain is the entire space H, so there is an empty intersection between the domain of F and the domain of G, the interior of the domain of F and the domain of G. So here I can, first I need to multiply by, just for convenience, for a gamma, for a step, and then I can split the sum. So this is equivalent to say that 0 belongs to gamma, the gradient of F. So I use the fact that if the function is differentiable, the subdifferential is a singleton and coincides with the gradient, plus gamma, the subdifferential of G at X star. Okay. And then what do I do? This means that I take this on the other side. So I have that minus gamma the gradient is in the gamma the subdifferential of G, and now I add on both sides X star. And so what I get is this vector, X star minus gamma the gradient, is in identity plus gamma the subdifferential of G at X star. So what I can write is that X star is the prox of gamma G of X star minus gamma the gradient of F at X star. And this is the fixed point equation, which is satisfied by all the minimizers. Okay, so more precisely, what can I, so now that I have a fixed point equation, I can think of iterating this mapping. So I define T gamma equal to the prox composed with identity minus the gradient. And then I can define an iteration by setting xk plus 1 equal to T gamma of xk. So as you can see, this is another example of fixed point iterations that we saw in the previous lectures. So at this point, I can say many things. First, so the thing that we will have to do is to prove that this T gamma is an averaged operator, so that we can rely on all the convergence analysis and derive convergence results. Spoiler, so T gamma is the composition of these identities minus gamma the gradient, which is gamma L divided by 2 averaged. We proved this last time, composed with the proximity operator, and we will prove that the proximity operator will be averaged as well. And then we need to prove to have a result on the composition of averaged operators. And this will be the roadmap in order to prove convergence of the function values. Instead, of the iterates. For the convergence of the function values, we will have to rely again on the descent lemma and do computations, basically. Other things that I can say is that, so you immediately see from from this expression why this algorithm is called the proximal gradient. So we have a proximal operation plus a gradient composed with a gradient descent step. And very often this algorithm is called proximal gradient splitting algorithm. And this put the algorithm in a wider family of the so-called splitting methods. And the splitting in the sense that, as you can see, you split the contribution of the smooth part and the non-smooth part. You exploit smoothness. So the smooth part is activated through the gradient. The non-smooth instead is activated through this nonlinear operation, implicit, maybe difficult to compute, but they are splitted. And so this again is a line of research. So splitting methods, as you can split. So instead of considering the sum of two terms, you consider the sum of many terms. You put linear operators, and the splitting methods try to split everything. So to activate each component individually. The other name that you can find around is forward-backward algorithm. This is also called forward-backward, and the idea instead is related to, in this case, discretization, because this forward step in which you do an explicit discretization, and the prox, as we saw before, corresponds to an implicit discretization. And again, this is the name that you can use where you replace this prox that we have seen is a resolvent of a maximal monotone operator, and this one can be instead, if you have a monotone operator, single valued, you can do this, let's say, gradient descent step. So it's the name. It is the name that is used in a most general scenario. So if G is equal to 0, you get back the gradient descent, and the results that I will derive are in a sense tight, because when you specialize to the case G equal to 0, you get the convergence rates that you can prove for the gradient. And instead, if f is equal to 0, you get back the proximal point algorithm that we have seen before. So it's a generalization of both. When you apply, when you apply this to the lasso that I just erased, so you get, I do the example before so that we have some kind of motivation. So you get S gamma. Okay, so you get an algorithm like this. And here I need regularizing, regularizer. And so as you can see, this is a bit what I was saying at the beginning. This is a first order method. And what if you have a square loss, so a quadratic term, what you need to do is just matrix vector multiplication. And then you need to apply this operation, which is even cheaper than the gradient. So here the oracle, which is costly, this gradient step. The other one is for free. One good thing on which maybe I will insist a bit later is the fact that at each step you apply a soft thresholding operation. So at each step, your iteration will be, let's say, sparse in the sense that it means nothing, but every time that this vector is as components which are less than gamma, lambda, in absolute value, these components will be put to equal to 0. So this is very nice from the implementation point of view, because you don't need to set the thresholds and to say, if I have some components which are epsilon, but what is epsilon? So it's 0 automatically. So this is a very nice feature of the method that gives you zeros at the iterates level. Okay, so with this in mind, I'll try to give all the tools in order to prove convergence. So as I was saying, here we have, so first I focus on, I prepare for the convergence of the iterates. Here we have this one, which is alpha averaged. The proximity operator is 1 alpha averaged, so is firmly non-expansive as the projection. So proposition, if f is so now I get back, I try to keep G. meaning that is 1/2 average. So can be written as 1/2 the identity plus 1/2 a non-expansive operator. And the proof, so I was planning to do it, maybe I skip it because otherwise I want to do stochastic gradient descent, because otherwise it's a problem. I know that somebody is waiting for it. So I just skip the proof. The proof is based on the subdifferential characterization. So you need to exploit the fact that P is the prox if and only if x minus P over gamma is the prox if and only if x minus P over gamma is the subdifferential of G of P. And then you write it and you get firm non-expansivity. The second tool that we need, the second result that we need is this is non-trivial at all, and is the fact that the composition of alpha averaged operators is still alpha averaged, and more precisely is like this. So let T1 be, so from H to H, be alpha 1 averaged, and T2 be alpha 2 averaged. Then T1 composed T2 is, now I check because otherwise I write it wrong for sure. So if T1 is alpha 1 average and T2 is alpha 2 averaged, the composition is still averaged, and this is the constant of averageness, okay? And this is quite recent, again, as a result, I think 2015 or something like that, by Combat, which is a name to keep in mind for sure, maybe. And someone else, I think, in the paper, because there was another constant was known previously, which is less tight. So this is the best result available. And so if we do the computations, I skip them. So if I do the computations, what I get, I should put alpha 1 equal to 1/2, and the other is gamma L over 2. Then T gamma, which is our prox composed with the gradient, identity minus the gradient, is 2 over 4 minus gamma L averaged. And of course, to have this equality, I need that identity minus gamma, the gradient, is averaged, so I need gamma to be less than 2 over L. Or gamma less than 2 over L, otherwise it's not true. Yeah. Okay. Okay, so this already gives us more or less everything. I need to write the theorem, the convergence theorem. So if you agree, I will skip the assumptions, so are the ones that I wrote at the beginning. The gradient of f is a Lipschitz, and the other one is just gamma 0. And then and the set of minimizers is non-empty. So the proximal gradient algorithm satisfies the following things. One, this is true for every starting point. So this is again the nice thing of convex optimization. If you remember this quantity, so we know how to bound this quantity in terms of the averageness constant. We did it for a general averaged operator. So I write here what we get for this special constant, but is a result that we have already seen. Okay. And then the other two results are two. Let me give a name to F plus G, because otherwise the formulas are too long. I call it big F. What I have is that f of xk is decreasing. So this is a descent algorithm. And f of xk minus the minimum of f is indeed a small o of 1 over k. And again, this is a recent observation, even if it's elementary. And moreover, so I can be more specific. Instead of writing a small o, I have a quantitative inequality as the one that is I wrote for the gradients or the subgradient. And f of xk minus the minimum of f is less or equal than. Here I have to put the Lipschitz constant of the gradient, the distance, sorry, no, I do it in general, so no, it's all wrong. So the initialization error, so the distance of x0 from the set of minimizers, and this gives me the convergence rates. So the number of iterations, the convergence rate is called sublinear and decays so polynomially as constant over k times a constant which depends on the choice of gamma. And in particular, there are these two cases. So there is one case that is the case where gamma is smaller than 1 over L, and the other one, which is the case where gamma is between 1 over L and 2 over L, and this one is okay. So again, so maybe, and then, sorry, the last result is that the sequence of iterates converge and converge weakly to some minimizer of f. Okay. So this one, we already did it, so I do not comment anymore, and also the first one. Maybe the only things that need to be commented is this. So this is a convergence rate of the function values. These are the typical rates that are used in machine learning, not the convergence of the iterates, as I was saying. Even if for sparsity-based regularization, so where we care about the structure of our solution, these become relevant, okay? In the sense that, for instance, I would like to know that if this has certain non-zero components, also this one has the same structure because I'm using it as an approximation. So this is this is one of the cases where this third condition is more interesting. Other comments, so this is a convergence rate 1 over k is called, and so it's the same that you can derive for the gradient with the same, so the same that you can derive for the gradient. And other thing, you have a constant that depends on the choice of the step size. The optimal choice that you can do is gamma equal to 1 over L, okay? Why it's interesting to consider gamma bigger than 1 over L? This is I don't know, this is often done, for instance, in the convex optimization community, while in machine learning, you use this. Because in practice, you like to take steps as long as possible. So the speed of gradient descent depends on the choice of the step. So having a bigger interval to choose the step size is good. Okay, but you cannot prove in practice, in principle, that this is a better choice. So the best choice, that the choice that minimizes this upper bound is gamma equal to 1 over L. This algorithm is often called that take his name from I didn't say from this case specifically, is called iterative soft thresholding. So you take ISTA. And I don't know. So maybe, I don't know, I propose to, if you agree, maybe you can choose. I would propose maybe to skip the proof. The proof is, we can do, it's instructive in the sense that I can do it also in the other hour as you prefer. In the sense that so we need to prove the second line. And the proof is, as always, as these proofs in optimization, is very similar to the one that we did for the gradient under the Loyasiewicz assumption. So you start from the descent lemma, and now you have to combine if you want, the only complication is the fact that you have to combine it with the existence of the prox. So you need to use the prox definition, but more or less the spirit, I would say, is the same. So maybe it's meaningful because I'm saying this because I'd like to do in the last 1 hour and a half to try to explain the stochastic gradient descent and possible accelerations. So maybe I just add, since we have still 5 minutes, I just add some comments. So so this is it's called, all these results that I'm giving are called worst case convergence analysis, worst case convergence bounds, in the sense that these results hold for every convex function which satisfies the assumptions. Okay, so it's a worst case convergence upper bound. This is true for every f. Okay, even for the worst f in the world. So a lot of effort has been devoted instead to the study of specific classes of functions that satisfy some additional assumptions. Because in practice, for instance, this iterative soft thresholding is much better than, behaves much better than this convergence rate, which is not very good. And the classes that have been considered are exactly the ones that satisfies not the Polyak Loyasiewicz or Loyasiewicz, but the Kurdica Loyasiewicz, which is the generalization to the nonlinear, the non-smooth setting. So there is a, let's say, a trend of analysis under the KL. Kurdica, I don't know if it's correct, Loyasiewicz inequality. This has been done both in the convex and non-convex scenario, and maybe everything started by a paper by Attush, Boltes, Weiter. And then there is, and in particular, so let me say that in particular for this algorithm, for instance, you can prove linear convergence, for instance. So this is much better. You can prove linear convergence, and you can prove even better results, in the sense that you can prove that the iterates xk, so if you assume, so if you give a definition to the, if you give a name to the support of the minimizers of the regularized problem, so you can prove that the union of all the support are sorry. So I have a minimizer, and this minimizer will have certain non-zeros. So the support of this minimizer will be the set of i's such that x star I is different from 0. Okay. You can compute this, so you can consider this support for all the minimizer that you have, because in general you will not have a unique minimizer. You can prove that you give a name to this stuff, and this is even in the infinite dimensional case where you consider sequences is small L2, this is a finite set, so the union of the support. And at the end, what you show is that your iterates, after a finite number of iterations, have the support which is contained in this union of supports. So this is called the identification result. And this is very useful, as I was saying before, because you want to have an approximation of your ideal solution which respects its structure. So this is another So we worked on this both with, in particular, I have to name Guillaume Garrigos that worked a lot on this stuff. And then again, for instance, another name, Fadili Peyre, that worked on these kind of properties, identification properties of proximal gradient methods. And that's it. The last thing instead that I want to say is the fact that there is a complexity theory that was started, as I was saying, maybe not started, but I don't know, formalized by Nemirovsky and Yudin, that allows to define the class of so-called optimal algorithms, meaning that if you fix a class of functions to which you apply an algorithm, you can find lower bounds. So if I say I apply algorithms that that use only the gradient, then I know that on the class of convex functions with Lipschitz continuous gradient, I cannot do better than not constant over k, but constant over k square. And so this is the gradient, the proximal gradient is not an optimal algorithm in the sense that achieves a convergence rate which is just 1 over k. So in the next lecture, I'd like to divide it in 2 parts. In the first part, I'd like to mention a bit these accelerated methods, because again, has raised a lot of interest and they have been used so much. And the other one instead, the stochastic direction. So I would stop here. I don't know if there are questions.
Thank you very much. Are there questions, comments? No, apparently not. Eh? Yeah, no, maybe she's been too clear. So thank you. Okay, so we can resume with the last part of this series, a wonderful series of lectures of Silvia that let me learn a lot about optimization. So please, and thank you.
Thank you, Simone. So I'll try to, as I was saying, this last lecture is devoted to possible extensions. So there are many possible extensions of what I said in several directions. So I maybe present the ones that I know better, and of course, stochastic gradient setting, because it's the most relevant one nowadays. So first, one ingredient also of the recent stochastic methods that are used. So I don't, disclaimer, I do not, so I tried to study a bit Adam for this lecture. So I never implemented it, I never used it. But so the Adam name, so this is a bit my motivation for this last lecture. I want to study this once or the other time, in the sense that the Adam algorithm, I had a look to the original paper that is by Kingma, and I don't remember the other author. So this paper has another one, has like 130,000 citations. That for an optimization paper is pretty good number. So this is not just to advertise this paper, but just to say that these kind of things had a huge impact. So this was unbelievable 20 years ago. So this is due to the applications in the deep learning setting. And so the two things that are here are, so this is a stochastic method. So I will try to talk about stochastic gradient descent. It's called stochastic GD, SGD. And then the other things, so I start from the M, momentum, and this is related to accelerations. And this is I will start from here. And yeah, the last one, which is the one that I know less, so I will let it for the end, is the adaptive. So the novelties with respect to what we have done is the fact that we need to move to the stochastic setting. We need to accelerate, and this will be done through this momentum. And this adaptive instead is related to the choice of the step size. So the choice of the steps, as I mentioned this a couple of times, is tricky in the sense that you have to know either the Lipschitz constant of the gradient, or in the strongly convex case, if you want to do the optimal choice, even the strong convexity constant. So this class of methods instead try to avoid this choice and to set the step automatically, and depending on the place where you are. So I start from the accelerations, because this has been developed for in the non-stochastic setting. So accelerations. As I was saying at the beginning, at the end of the last lecture, so the gradient method in itself is not optimal. There was this complexity analysis, so we know what is the best we can achieve is 1 over k square. And so there have been really a huge effort to reach this optimal convergence rate. And the first idea was due to Polyak. And the first, let's say, accelerated method in the 80s, the first accelerated method is called heavy ball algorithm. So I write it in the smooth setting, but it can be extended to the prox. Just write the prox in front of the gradient step. And so it looks like that. So let me write it in the right order. And then so the idea is to have something very similar to gradient descent. So the first step is a gradient descent step. The only modification is this yk here, in the sense that instead of doing xk minus gamma the gradient, you take the direction of the gradient at xk, adding this xk plus 1 minus xk. So in a sense, this is called a multi-step method, in the sense that you try to keep into account the direction at the previous step in order to determine the one at the next step. So why it is called the heavy ball algorithm? So I'll try to derive this method. So I will not do it, but I will tell you how to derive it. This comes from a physical analogy, in the sense that as the gradient descent we have seen can be seen as a discretization of the gradient flow, this algorithm can be seen as a discretization of a second order equation, which is like this. So I'll write it and then we comment it. So I should put, how do I call it? P. So what should this should be F equal M times A, where the mass is 1, and should describe the motion of a heavy ball, so a point with a mass that is sliding, let's say, and is not, so it's sliding on the graph of F, so, and as where there is a force that is against the movement, so it's like a friction, which is this one, so it's proportional to the velocity. So this is called, there is this friction. What is the idea is that when we do a gradient flow, think to, I don't know, a cup and a small steel ball. If you do the gradient flow, what will happen is that you will zigzag around the minimizer, the global minimizer. The idea is to add friction in order to avoid this zigzagging effect. This was a bit the motivation of why this should be reasonable. Yeah.
I mean, which is the relationship between P and beta?
Yes.
Are they?
Very good question.
Okay.
Very good question.
Okay.
So yes, there is a relation. Of course, this beta depends on the p, and so I will not do it. But in our notes, we did all the computation. So you can discretize it. If you discretize these equations, so you do the second derivative, this first one, you get exactly the relation between p and beta. And now, so there is a relation, and indeed, so what here is a friction, here is called inertia, in the sense that instead you keep going a bit in the direction of the previous direction. And so what happens to this algorithm? You can prove convergence, and in particular, the analysis of this heavy ball method has been done in the 80s by Polyak. It's even in his book, in the optimization, that I didn't advertise, but it's super nice. So the acceleration of the algorithm depends on the choice of beta, and happens only in the strongly convex setting. So I write the theorem so that I'm a bit more concrete. So the theorem is this one. So I need to take F, which is strongly convex, and with the F mu strongly convex, L smooth. Then I know that there is a unique minimizer, and I can write the following thing. So this is let's say a corollary of the Polyak theorem, but I prefer to simplify a bit. So this is related to your question. So this is the this is a step size, and now this is related to your question. Let's say this is the optimal choice of the beta that let's say is related to the optimal choice of p. So not any friction is fine. So the viscosity should be wisely chosen, and this is chosen depending on the Lipschitz constant of the gradient of f and on the strong convexity parameter. And the bad thing is that, as you can see, this inertial parameter depends on the strong convexity constant. That is very difficult to compute. So this is bad. But in any case, if we are able to do these choices, what happens is that you get an improved convergence rate, in the sense that xk minus x star is less or equal than sorry. So maybe I think that in the standard for gradient descent, maybe I wrote it with the square. I don't know. So we have to compute it. So, but the comparison is in order to compare the convergence rate of this method with the one of gradient descent in the strongly convex setting, we should compare these two things. So this is the one that you get for the gradient. This is the one that you get in this case. And you can prove that this is always smaller. And again, there are results that tell you that you cannot do better than this. So this is the optimal method for strongly convex functions. An optimal method for strongly convex functions. So, okay. Second step. Now, almost nobody. So this is really the idea. I think was due to Polyak. The point is that when you apply this inertial method to this accelerated method, which is called, so these methods are called, depending on the people, inertial methods, accelerated methods, or momentum-based methods. So if you apply this method to a convex function, smooth, you do not gain any acceleration. so I don't know. So the proof of convergence is even recent. So I don't remember. I think there is a paper by Gadini and collaborators. I think it's 2013 or something like this. I would say something like this. And so which proves convergence of the heavy ball in the convex setting. But what you get is a convergence result which is exactly, not exactly, but apart from constants, is the same as gradient descent. So there is no interest in using an acceleration because it does not accelerate. Let me note, I didn't do it before, from the computational point of view, this is equivalent to gradient descent. Okay, there is no additional computation, there are no additional computations, it's just a sum of vectors, so zero cost. Okay, so that's when, let's say, Nesterov came into play, again in the 80s. And so what he did is that he did a small modification of this algorithm. And in particular, the modification is the following. So there are two modifications. So the structure of the algorithm is the same, but what Nesterov did is that the gradient is not computed anymore in the previous xk, but now is computed in this linear interpolation of the previous two iterates. And the thing here is not constant anymore, but is variable in time. And more precisely, for instance, so the expression for the original Nesterov formulation is not involved, but it is a recursive formula. More recently, now it's easier to use. This is let's say the classic. This is an expression for beta k, which is equivalent to the Nesterov one, and is mostly used today because it's easier to compute. So these are the two modifications of Nesterov, and with a complete algebraic proof. So it's really cannot be understood why it works while you accelerate. Many people try to understand why these algebraic manipulations give a better convergence rate. You prove that on convex problems. So I can write the same theorem. Sorry, I write it later. I do some more comments before. You can prove that these accelerate on convex in the convex setting. This is worse than so in the strongly convex setting. Still, you need to take beta constant instead, like this. And so, as I was saying, the original proof is due to Nesterov and is completely algebraic. So you don't. There are algebraic things that work and give you the convergence rate. More recently, people tried to interpret this Nesterov algorithm as a discretization of this of a second order differential equation, which is similar to the one above. And maybe the thing that made so also the French ones were working on this, but I have to say that the first paper where the analogy was made is this Boyd-Candace paper, and and to be more precise, even so the idea is this one. You have still an heavy ball motion, but now the friction is not constant anymore, but goes to zero as time goes to infinity. So the idea is that you slow down the convergence at the beginning, but then when you're close to when you're close to the minimizer, the friction goes away. So this should allow, in principle, to go faster to the minimizer. And to be more precise, the original proof is in a very specific case. Is in the case alpha equal 3. And then after this, it has been generalized to more general cases, and this is the same 3. And you can see how these two, again, are related. You can do the computation, you get exactly this. There is just one thing that I don't like, and maybe more recently they try to fix this. So the point is that this is a discretization of this, But as you can see, the gradient of f is computed at yk. So it's neither xk nor xk plus 1, is this yk that is this one. So saying this, that this is a natural discretization of this equation is a bit of a stretch, in my opinion. And if you do different discretizations, it doesn't work. So let's say there has been a lot of work on the analysis of these of the solution trajectories of this continuous time equation, trying to explain why this algorithm works, but in principle, this would explain both this one and that one, right, with a beta k. So still the why in the discrete setting they behave differently is not completely understood, even if there are still things, many things going on here. So they are trying to explain this better. And what you get is the following stuff, the following theorem. Yes?
Okay. But so Nesteron came up with this modification by luck.
But I don't know. So he was using this machinery. At the beginning, I found it very enlightening, and then you got, I think, he was using this idea. He was using this idea of he called them estimate sequences. So the idea. So now I don't know if I'm able to write them. In any case, you have to solve this minimization problem. You replace it with a quadratic objective, which you know how to minimize, and these are really quadratic, so you know how to minimize. And you see, and you, so the point is that in order to have, to have this sequence, sorry, I try to write it, I'm not sure it will be, so take it, so it should be something like this. So I'm not sure, so don't write it, just, so this would be the idea. In order to write, to find the next, so you at each step you minimize this approximation of the original function, and in order to have this shrinking, you have an update rule for this estimate sequence. And the fact that this inequality should be satisfied gives you an update. So he has an update rule for this pk plus 1. And what you see is that at the end, so it's the algorithm is written in a different form with a different parameters. So it looks different from here. But what you get is something that looks like that at the end. So it was a completely different point of view. Then, since these estimate sequences were not clear, so that it was not clear how you did this, why you do these choices. I would say 20 years later, so this first paper by Nesteron was completely forgotten by the other people, and then it started to be cited 20 years later with the, and I tell you also when. And so people tried to understand what was behind this estimate sequence procedure. And they come out with this interpretation that made the analogy between the Nesterov method and the heavy ball by Polyak method that was much more transparent in a sense, at least as a motivation at a high level. And then at the end, after this, also the proof. Now, the most transparent proof is based on that interpretation in the sense that you build a Lyapunov function and you show that this is decreasing along the iteration. So again, why you take that Lyapunov function is not completely clear, but at least it has a physical interpretation. Okay, so yes, I don't know how we did it.
Okay. Okay, thank you.
So, yeah.
No, just a curiosity. Usually when you discretize and you have the second order derivative, for example, which kind of finite difference have been used?
The classical one, that should be
Second order.
xk plus 1 minus 2xk.
Yes,
xk
yes.
1.
In fact, my question is that I don't see, for example, xk minus 1 or the step size square, because usually when you use this kind of.
To do some steps.
Ah, okay.
So I would not do all this computation because I don't
Yeah,
remember.
no,
But
yes,
thank
but just
you.
as a
I'm
curiosity.
as curious as you, so I did them. So and you
Okay.
in the notes there are all the derivation step by step to arrive from the continuous discretization of the continuous equation to the algorithm.
Okay, thank you very much.
You're welcome. And so maybe the other surprising fact that I didn't mention is the fact that it was not known. So this let's say this complexity result by Nemirovsky and Yudin tells us that there is not a first. So you cannot do better than constant over k square of that or that rate in the strongly convex setting using the gradient at the current step plus all the previous gradients. So the other, if you want gain that Nesterov did or Polyak did, is the fact that you can be optimal using only 2 previous iterations. So you don't need to keep track of all the memory. So there are, again, momentum-based algorithms that keep track of all the previous gradients. So they do an average of all the previous gradients. In order to be optimal, you need just 2 of them. So the maybe the theorem is like that. So now F is just convex, so convex and with the differentiable with L smooth. So X star is a minimizer, which I assume to be non-empty. Then, so here I need to take first thing gamma smaller than 1 over L. Then I can do this stuff. I can prove this stuff. F of xk minus the minimum of F is less or equal of the distance between x0 and r minus f squared divided by 2 gamma k square. So the gain is this k square here instead of the k. Then the other thing that I should say is that this is the original choice of beta k. More recently, what they do is that they put here k plus a bigger or equal than 3. And what you can prove is the following, that if a is bigger than 3, then xk quickly converge to some element in the set of minimizers. So the convergence of the items for the case k equal 3 is still open. But we don't know if in the case k a equal 3, the iterates are convergent or not. The convergence of the function values is known even for a going to 0, so it's degraded, it's not like this. So this is for a bigger than 3, you get 2, but before you go to 1, so you pass from the non-accelerated to the accelerated. But instead, you have convergence of the iterates only in this case. And the proof, as I was saying, is based on a Lyapunov argument. So you define, if you want, I can write, but maybe not. So you just define a Lyapunov energy, which is based on the function values plus a square norm, which is not clear why it's that one. Okay. And so this is maybe a bit of a picture of accelerated methods. So the most famous, the most famous accelerated method, I think one of the most famous I should mention is FISTA by Beck and Tebull. So, the proximal gradient in the L1 case is ISTA. So this is the fast ISTA, and again, this is a proximal is an accelerated proximal gradient. So you can put a proxy in front of the gradient step. And you can do exactly the same result. And again, this was the one very influential paper. I think it has 12,000 citations, something like this. So these are incredibly, so it's quite, always surprises me in the sense, these are first order methods. I mean, the gradient, we know it since 200 years more or less. And, but these were had a huge impact in the signal processing and machine learning community. Okay. So one thing that is instead bad of the accelerated methods that they do not behave so well with the geometrical assumptions. So you know you have this good convergence, the strongly convex case. This convergence in the convex case, it's not so clear how to deal with the Kurdi-Kaloyazievich assumption, even if there is again a line of work going in that direction. And this may be the, I don't know, the people working on this are Ojol, Dossal, and Chambol. Dossal. So Chambol was the first one together with Dossal to prove convergence of the iterates. So to understand that the key was to change a bit the coefficients in order to gain something and to have convergence of the iterates. So the result was due to Chambol and Dossal. And still, to prove convergence of the iterates, you use OPL lemma. You don't use anymore the fixed point stuff, but the OPL lemma, yes. Okay. Last maybe comment is that where are we going? So I was thinking to have this last lecture where I also give you some, I don't know, my impressions on where people are going, what are they studying now. Since the FISTA paper is 2005, so it's almost 20 years ago. No, maybe 2009, so less. I was a bit impressed by 2005. Okay, 2009. And so what people are doing now is what they call, in this direction, is what they call Eshelman-driven damping. So the idea is that this choice of the friction, that is alpha over t, can be improved by putting instead a function that depends on the second derivative of the function itself. So it's something like this. They study, so they still put the alpha over t, but then they add gradient square prime plus so they study something like this, and then when you discretize here, you get a finite difference. So instead of having only xk plus 1 minus xk, you also have gradient of f xk plus 1 minus gradient of f of the at xk. And this gives, in practice, if you look at the pictures, is better in the sense that is less oscillatory. The accelerated methods are not descending methods, and you observe very often oscillations. And with this correction, let's say you avoid, you try to a bit avoid them. And yeah. Okay, so now I finish with the acceleration part. So I should tell you something about the stochastic gradient, SGD. So the setting is the following. I want to minimize a function f, and indeed here, to be more precise, this is always called stochastic gradient descent. This is the this is the name that is inherited by the machine learning community, really. To be more proper, this would be a stochastic subgradient method, because it's not a descent method and it's not a gradient method, it's a subgradient. The setting is, the classical setting is where f is just not gamma 0, even less than this, in the sense that goes from H to R, convex. Okay. And then the algorithm is like this. So you take an initial point, and then you define an iterate like this. So this will be a stochastic algorithm in the sense that this is an h-valued random variable. So let me assume I decide h is finite dimensional, so that I don't have expectations in an infinite dimensional setting. So there are many results in the infinite dimensional setting if h is a separable Hilbert space. So you need separability. So you have this. So you assume, so it's clear that we assume less. So here we assume at each step, instead of using the subgradient of a subgradient of the function, we use a random vector, which in expectation belongs to the subgradient of the function. Okay. And so the results that we will see are convergence results. So here I'd like to prove the theorem, because it covers the subgradient algorithm, which I didn't prove. And the proof is, again, elementary, and is the one that is all used everywhere. So I will need to take gamma k moving, so I cannot take gamma fixed. And what I want to say, yes, I will need to study again this quantity like this. So the algorithm is not descending. The expectations, the convergence results will be in expectation. We can discuss if this is meaningful or not, but the classical results of convergence are in expectation. So we don't know what happens when we will run the algorithm, okay, on our single run. Okay, or the other one, which is the same as the subgradient method. So f x bar k, I need to define the averaged iterate. The sum of gamma I. So we will, the results that I state hold for the best iterate or for f evaluated, for the expectation of f evaluated at this averaged iterate. I proceed in a mathematical way. I state the convergence theorem, and then I do the examples, okay? The general result, and then I do the connection of what with the empirical risk and the risk that I promised at the beginning, so 2 days ago. So I need to assume all these, so let's assume all these assumptions that are on the blackboard are assumptions. I need to ensure that there exists a minimizer, so even if we can say something when it does not exist. Then the assumptions on the random vector is that is bounded. So I think this one is enough. No, I need it. No. I need to assume this. If you remember, even for subgradient descent, for the subgradient algorithm, I was assuming that the subgradients were bounded. So this is the same setting. Okay. Then So let me write. Let's see. Here I can put gamma k. So the expression, if you remember it, I'm not sure, but it's exactly the same as for the subgradient method, exactly the same inequality. The only difference is that here we have the expectation. So x star here is a minimizer. And this is true for any x star in the set of minimizers. So I can upper bound this with the distance from the optimal set. There are, let's say, I will skip in the proof the summability part, so I will take conditional expectations. I will not check that I can do it, but we can do it. So, and yes, so from this, sorry, just the last thing, but these are considerations that I already did for the subgradient. This gives us prescriptions for choosing the step size. So the step size will be again of the form constant divided square root of k, square root of I, right? So I will need to take a decrease in step size, and this will be the optimal choice. Okay, cool. And another thing that I didn't stress enough is the fact that I didn't write that the sequence of iterates is convergent almost surely, in the sense that, I don't know, so I was not able to find a result stating this. So there are results for almost sure convergence of the iterates. So we have a stochastic Copial lemma. This is available. But the only cases in which I have seen weak convergence of the iterates are in the strictly convex case. So you need to assume something more on the function, strongly convex, obviously. And the other case is where you don't have something like this, but you assume more on the stochastic approximation. And so in the general case, so I don't know if it converges or not. Okay. So how do you prove it? So you start from here. So you take an x, an arbitrary x, and you write this, and you just develop this the square. So this is xk minus x square minus 2 gamma square xk, so xk minus, be like this. So it's xk minus gamma, okay, plus gamma k square uk square. So I just use the definition of xk plus 1. Then what do you do is that you take the conditional expectation with respect to xk. And so you have a of xk plus 1 minus x square conditioned to xk is equal to. So when I condition to xk, this function is measurable, and so I have xk minus x. And here again, this is measurable, so I can move the expectation inside the scalar product, and I get plus okay. Now, what can I do? Here, this condition is the definition of the algorithm. This conditional expectation, this should be an element in the subgradient of, in the subdifferential of f. So this belongs to subdifferential of f at xk. Therefore, I can use the subgradient inequality, the subdifferential inequality that tells me what, so let me write it because otherwise, let's give a name to this vector, let's call it UK. So I have that UK xk minus x, and I put the minus already in front of it that I have. So it's equal to, sorry, I'm slow, but because otherwise I will write it wrong. So this is less or equal than f of x minus f of xk. Okay. And then I can replace this here, and I get, okay, I rewrite it. Plus gamma k square e of uk square given xk. Okay. Now that we have this inequality, I can take the expectation, full expectation, and then what I get is that here I get e of xk plus 1 minus x square is less or equal than e of this minus 2 gamma k f of x minus e of f of xk, and then here plus gamma k square e of uk square. And now, so far so good. Yes, so I take this one and I bring it on the other side. So I have 2 gamma k e of f of xk minus f of x. This is less or equal than this minus this. Plus this, which I can upper bound with b square. Because I assume that the subdifferential were bounded in expectation in order. This assumption here. So and now I can take the sum. Here I have a telescopic sum because I have the same expectation in both cases, and I derive exactly what I wrote. Okay, and this is the proof. That's it. So this works, as you see, in the for subgradients. So you don't gain much if you assume differentiability of the function. So if we try to make a parallel to the deterministic setting, we saw that the subgradient method converged as, let's say, let's forget the logarithm, 1 over square root of k. The gradient method as 1 over k. So you gain by assuming differentiability of the function. Here we see that even if we assume differentiability, you don't gain anything in terms of convergence rates. It changes something in terms of the assumptions that you can make on the stochastic estimate. So yes.
Are there any results regarding the variance of the distribution of
yes,
the convergence?
So yes.
Oh, okay.
So they start to be there start to be some results. I've not read it yet. I think there is a recent paper by Saverio Salso and Andrea Paudice. Yes, trying to understand a bit this. There are almost sure convergence results which are asymptotic, are not so. So I don't know. Okay. I don't know. I was thinking they were great, and then I'm not sure. And yes, and there is another instead direction, very big direction, which I skipped completely today, which is instead the direction of variance reduction, but not not of the algorithm, but of the estimate of the stochastic gradient. So here we don't assume. So what I So let me see. I write it for the smooth setting, and then I tell you what you do.
Okay.
To improve. So in the smooth setting, what you assume is the following. Instead of assuming that the subgradients are bounded, if F is smooth, I do this again. I do the smooth setting. I could do the prox, but it's the same. Okay, it's for Roberto. If F is L smooth, then you can do a similar proof, let's say, where you assume that you have this bound on the variance. So instead of assuming that the U at K's are bounded, you can bound, let's say, the distance of the estimation from the gradient of F, from its expectation. Okay. And so this is what you, in this sense, this quantity, so along the iterations, this quantity does not go to 0, but is constant upper bounded by sigma square. And this is exactly what happens when you apply SGD to empirical risk or expectation or minimization of the risk. Now I show you. And instead, there is a whole class of so-called variance-reduced methods. Where instead you change, starting on this, you try to build a new approximation of the gradient for which this quantity decreases along the iterations. And usually how you do it is by averaging past information, for instance. So the methods, I don't know if you ever seen them, these are SVRG, stochastic variance reduced gradient, SAGA, I don't know, stochastic something, but it's more. SAG is another one of these setting. MISO, I think another one is Finito. So all these methods, let's say, are different. They have differences, but rely on the idea of try to reduce this variance. In this sense, you can obtain much better convergence results in the sense that you can recover the results that you have in the deterministic, let's say, the convergence rates that hold true in the deterministic setting, although you still get convergence rates just in expectation. And you can choose a constant step size, which is great. Small, but constant.
But like, I have another, let's say, question. But like here, I see that the noise is basically inside the. I mean, I in principle, I could simply add a Gaussian noise to my UK and it would work, right? Are there any results where the noise is induced by the sampling of the data?
Yes, yes,
like,
yes.
Okay.
And this is the point that as I was saying at the beginning. The main example. So in machine learning, the main example is this one that I'm going to do now.
Exactly. Okay. Thank you.
And it's not like that. It's not that I add noise because I want to do it. Even if this may be beneficial in studying the non-convex scenario. So this is another direction again, but I don't. So, okay, so instead, the application for, so let's call it SGD for empirical risk, is this one. So we have seen that when you want to solve a machine learning problem, very often you have to minimize. I write it in the optimization way, then I further specialize it, I promise, like this. So you want to minimize say an average of functions, okay? Each fi is a function which is, let's assume it's differentiable with, I don't know, Lipschitz continuous gradient. Maybe, yes. And now I tell you the right assumptions. I need more than this. So this is convex, and I assume that is Lipschitz. Fi is Bi Lipschitz. Okay. Because I don't want, so I do this, so I will, it's the same, but I do the special case of the first algorithm that we, for which we proved convergence. Okay, then what do I need? I need to assume I take just for writing easily things easily, I define a selection of the subgradient, okay, of the subdifferential. So I give it a name, nabla tilde. Fi belong at x belong to the subdifferential of Fi at x. And then I can write, so what happens is that I can take as, if I want to apply, I obtain an instance of stochastic gradient descent if I choose, if I write the following algorithm. Where u hat k is equal to this element in the subdifferential of Fi, and this f is f, you see, so this is a subdifferential of Fik, so a special element in the sum at the point xk. So what do I do in practice? At each step, I choose randomly an Fi, a function, and I use the gradient of that function instead of the gradient of the entire sum. So if we think to a machine learning application where this n maybe is 1 million, it means that if I apply gradient descent, before doing my first step, I have to compute 1 million of gradients. So it may take a while, While here, what do I do? In order to do one step, I compute one gradient and I move. This movement maybe is not so effective as the one of gradient descent, but at least, I mean, it's a step. And this is also used a lot in the, let's say, online scenario where you cannot wait instead to have all the points, but you have them really arriving one after the other. So the classical assumption is how do you select this function is Ik should be uniform, a random variable which is uniformly distributed on the set 1n. So you choose the. Then if you do this assumption, so if Ik is like this, is independent from xk, and is uniform on 1n, when you take the expectation, you get exactly what you want. So if now I take the expectation of this nabla Fik xk conditioned to xk, what I get is that, as I was saying, this is independent from xk, is uniformly distributed on 1n. I get exactly 1 over n sum I1n. Okay, and now I'm safe since I assume that all the functions are defined on the entire space. This is a sum of subdifferentials, and then this is in the subdifferential of the sum. So this belongs to 1 over n subdifferential of, I didn't give a name, f. Let's call it f. So here, so this is called very often, this is called incremental gradient. This is the, I would say, this is, and sorry, I forgot one step, then I make the comments. The other thing that we have to show is that this thing is bounded. But this is easy because you, since the Fi are Lipschitz, the gradients are bounded, and the subgradient, so is bounded. And so this is at the end what you get is 1 over n. Okay, so this is the more, I would say, the most used form of stochastic gradient descent in machine learning. You don't have stochasticity in principle, in the sense that your empirical risk is a deterministic problem. You add stochasticity by yourself by the making this stochastic choice of the summand. what happens is that when you will do your infinite number of iterations, in expectation, you will arrive to a minimizer of the empirical risk. Okay. And so in the class, in the calculus, I'm sure you already seen it, but just to be super sure, if I change a bit the notation, since you know I like it, Fi of W will be L of W xi yi. So you will have a loss function that is fixed, and then in order to choose a summand, this means to choose a point in the training set. So you will randomly choose a point in the training set, you will compute the gradient of the loss with respect to that point, and you will go. And this is stochastic gradient descent, incremental gradient descent. Let's say if you have n points, every n points you call an epoch. So if you hear about epochs, what are epochs? On the training set, it means number of passes over the training set. So, and of course, since this selection is random, you usually divide it by the number of points, and you call them epochs. And you look at this descent, let's say how this quantity behaves after several epochs. From the, let's say that, from the implementation point of view, this algorithm is identical, at least each step of this algorithm is identical to the true stochastic gradient that would be the following. So now we remember that in machine learning, you really don't want to minimize the empirical risk, indeed, but you want to minimize something that is the risk, so the expected loss. And so in principle, your function is of the perfect form to be minimized with stochastic gradient descent. So let's try to do this very difficult thing. Well, maybe P. I don't know what Ernesto used, maybe rho. I don't know, rho, right? He likes rho, yeah. Okay, so you minimize these expectations. So you have already your function which is in the form of the expectation. And so I prepared everything precisely. Maybe it's good if I do it precisely. So, you can see that this function is a special case of more generally a function that you can write in this form. Okay, so I give a name to this pair xy, I call it z maybe, and I can write my function as let's say this integral which depends on a parameter. And this, so this is the framework that is usually studied many years ago in the field of stochastic. This is called stochastic optimization. This is the stochastic optimization framework. And basically what you do here is that here at each step, so you implement the gradient, the stochastic gradient descent in this form, where this u hat k belongs to the subdifferential of the integrand at the current iterate, wk, and evaluated at, let's say, at a variable zk, at the point zk, which is a realization of a sequence of copies, independent copies of z. So in order to implement this algorithm, you need vi, let's say I in n, so you need an infinite number of independent copies of z. So I can see, okay, this is a random variable and is like this. So I'm skipping, so because so you need some technical things in order to ensure that when you take the expectation of this vector, the conditional expectation, this belongs to the subdifferential of this f. Okay, so you need to pass the limit inside the integral. And so this is the true stochastic gradient descent. When you apply it to a machine learning problem, your ZK, your ZI, will be the sequence of points that you have in the training set. Okay. So when you apply stochastic gradient descent to minimize this problem, this original problem, at the end, what you will do will be the iterations that are exactly like this, where the only difference is the choice of the summand. Instead of choosing it randomly among your n points, let's say with replacement, so you can visit the same points many times, you do epochs using only these n points. Here, you are allowed to visit each point only once. So in principle, you will converge to the minimizer, to the minimum of this, only if you have an infinite number of points at your disposal that are independent. So this is the main difference, the choice of the index of the function that you take. For minimizing the empirical risk, many epochs. To minimize the expectation, one epoch. That's it. And this is, so that's what I'm saying. If you are in a very large, where you have many points, and then you can do many iterations, that's fine. Otherwise, usually you do multiple epochs. By the way, you do multiple epochs. This is the very rarely I've seen stochastic gradient descent with one epoch.
Yeah. So C is a random variable distributed like row, and
yes, exactly. Yes.
Okay. And
Yes.
why it is we have C con E in this size by H, not for example N?
No, yes, here I can call it as I want. That's the question.
Oh yeah.
So I need Z1, so I need an infinite in order to achieve, let's say, convergence.
Okay.
I need these ones which are as independent copies of Z. So they are distributed as row, and they are independent to each other.
Okay, thank you.
Okay, sorry. Those results hold for the convex case, right?
Yes.
So okay, so how many of them will I mean, if there are any, which also for the non-convex one?
No, so as they are, 0.
0. Oh, okay.
No, but so this was a bit strong statement, in the sense that usually the quantity that you study in the non-convex scenario is not the gap from the minimizer, but what you study is usually the norm of the gradient.
Okay.
In this sense, more or less, you get the results. Of course, with the fact that you can go to critical points and things like that. And the other, yes.
Because what I found personally curious is the fact that in my, let's say, career, I've always been introduced to those tools as a way to deal with non-convexity. Whereas here it is like a way of deal with a faster convergence. This was interesting.
Cheaper, maybe not faster, because in general you're not faster, but you are slower than using the gradient. That's the only way that you can do.
Okay.
Because you cannot compute a full gradient.
Okay. Yeah. Exactly.
To do it. Yeah.
Okay.
And instead, so I have to say that I know little in the non-convex scenario. So I don't know the results precisely, what you can say precisely in the non-convex setting, but for sure everything here doesn't work.
Okay. But still, it's strange because lots of ideas are the same.
Yes. The algorithm will look the same.
Yeah.
And so the problem that you have, so the first problem that you have in the non-differentiable case is that the convex subdifferential is very nice, and you need instead to use other notions of subdifferentiability. So usually in the non-smooth setting is used the Clark subdifferential is used. And what I can say is the thing that I was saying a bit at the beginning. It's not obvious how to compute the Clark subdifferential of a neural network, in the sense that the chain rule for the Clark subdifferential for the specific case of neural network does not hold.
Okay.
So you need to define other notions of subdifferentiability.
Okay, thank you.
You're welcome. Right. sorry. So okay, maybe just a few, just to, since there is still some time, I can say maybe few words on the. So I should say some words about the momentum in the stochastic case. So the bad news is that in practice it works better than stochastic gradient descent. In theory, you cannot prove a better convergence rate. And it's not that you are not able to prove it, is that there are lower bounds, and so 1 over square root of k is the optimal convergence rate. You cannot do better than this. What happens is that you improve the constants. You have two terms, one which is faster and the another one which is still of square root of k, but you cannot improve the rate globally. So this is one thing. So SGD with momentum exists, but the theoretical analysis is not so satisfactory as one would expect. So another, so we have, there are two ways, instead there are two ways to reduce the complexity of one gradient step. So one is this one where you have a sum structure and you use the gradient of just one summand. The other one is that when you have a function, when you want to decompose, let's say, the domain of the function. So the easiest case is where you have f from Rd to R. Let's assume it's differentiable. Then a trick that is used in practice is the following. So when you do the gradient step, xk minus gamma the gradient, it's a vector, and this vector is xk1 minus gamma the, let's call it, so the derivative with respect to the first variable, f at xk, and then, okay. Okay, and then the last one. So when here the dimension is very big, this may be very costly. And then what you can do is, instead of updating all the variables at once, you may decide to update just one of them. And so let's say this is called the coordinate descent. So in this case, the update is like this: xk plus 1 I is equal to xk I if I is different from ik. Otherwise, xk I minus gamma gradient I of x. So when you see this, you immediately want to do something better, because you see that here the step that you, so maybe I try to be more clear. So at each step, instead of updating the entire vector, I just update one real variable in this case. I can do it by blocks, maybe, but this is the idea. So when you look at this, you see here that you have the partial derivative of f, with respect, so the derivative with respect to the ith variable. And here you have a step size which is the same for everybody. And so here the first idea that the first thing that is exploited in order to get better results is the following: that geometrically corresponds to a preconditioning, if you want, of the problem. So if you have a function which is very anisotropic, so maybe it's very curved in one direction and very flat in the other, the step size will be very short, because it will depend on the Lipschitz constant of the gradient with respect to the steepest direction. But instead, in one direction, you can do very long steps. And so this is the idea. That's why here it's very helpful to use a different step size for any coordinate. And this makes a huge difference in practice, really huge. And in order to have convergence, what you can do is really to consider just the Lipschitz constant of the ith derivative with respect to the ith variable. So that's the Li. And you have convergence if you choose each gamma I less than this. So more precisely, in order to have convergence, what you need to do. So the point is that how you choose the next coordinate. So there are very many possible choices in the literature. Maybe the easiest one is the cyclic choice. So you fix an ordering of your variables and then you do it cyclically. The one which is, and this is nice in the sense that sometimes choosing a number uniformly from a very big vector can be, so this is maybe more true for the stochastic gradient where you have to take points uniformly. But even here, choosing you need to choose a random a coordinate uniformly at random. And so this is instead cyclic and you access to the things cyclically. And the convergence results are for sure, in the sense that there is no stochasticity. But the choice that is usually used in practice instead is a stochastic choice, where this coordinate is randomly chosen. It can be uniformly, or in so-called greedy methods, can be related to the descent that you observed in one direction. So you can choose the direction where you previously observed the biggest descent, biggest gradient, larger gradient. So, and these are the block coordinates results. So we worked with Saverio a bit on this. And what you can prove is that you can arrive here, and in practice, this makes a huge difference. The convergence rates that you can get, except for the constants that are different, are the same as gradient descent. So to really, this is the other case, and this allows me to introduce to the last ingredient, that is the ADA in ADAM, so the adaptive methods. There is a huge family of adaptive methods. And so the first one was ADAGRAD by Ducci and Singer. So, and in ADAGRAD, there are many ingredients. I will just single out one in order to present one, so that there are many reasons maybe why it works well, but I just want to emphasize one. So for sure, one that I will not emphasize, but is proper of ADAGRAD, is the fact that the step size is chosen according to the coordinate. So you do a coordinate choice in the original version. Here I will present the ADAGRAD norm. That is instead a method that is like ADAGRAD, but is not a coordinate descent, because it's easier to present. So the key ingredient, the key advantage of ADAGRAD is an automatic choice of the step size, as I was saying. So the algorithm, so you want to minimize x in h, f of x, and usually this is developed in the just convex and even non-convex, but let's say real valued setting. And the algorithm looks like that. So xk plus 1 is xk minus gamma divided vk gradient, so uk, where uk belongs to the subgradient of f at xk. So I forgot to check how should I choose gamma, which was my initial motivation. So, but I can tell you how it is updated. So this sequence is updated, and so this is the main idea, and it's clear why it's called ADAGRAD. Is vk square plus, so here we see the grad. norm of UK square. So basically, what happens is that, in a sense, you, I don't know, you accumulate the norms of the past gradients, and you can show that if the norm of UK is bounded, then this behavior is similar to the square root of k that is needed in order to have convergence of the subgradient method. So in a sense, it is an automatic choice. So this is the main idea. So in the original paper, this is done component-wise. So there is a modification of this idea which performs this operation component-wise. And so the analysis, so I struggled the last week to find an analysis in the convex scenario, in the convex setting, in the sense that I would say the most recent convergent results are indeed in a non-convex setting, in the stochastic case, not in this one. And the paper is a 2018 paper by Rachel Ward and Bottu. There is an analysis of Adagrad, but again, so every time, so these names usually refer to a family of algorithms. So very often in each paper, there is a slightly different implementation of the algorithm. The idea is the same, so basically the algorithm is the same, but it's difficult to match things perfectly. There is a paper which is nice by Bach and De Fossé, I think, which is a simple convergence analysis of Adagrad and Danam. So it's a meta algorithm for which, if you choose in the right way the parameters, you obtain both this Adagrad and the momentum. So it's a sort of Adagrad with a momentum, which is the final Adam result. So that's it. So sorry, just to conclude, in the convex setting, what you get again is nothing better than the standard implementation. This is always like this. What you in terms of convergence rates, you get convergent as the one where you choose in a blind way with respect to where you are the gradient, the step. But in practice, this can make the difference. Okay, so that's it.
Thank you very much, Silvia. It was very, very nice, very enlightening. So do you have questions, comments? Professor Villa, for this lecture, for the other lectures, for tomorrow's lecture by Saverio? If you have questions, you can ask.
You can ask Saverio tomorrow.
He's going to ask us Saverio tomorrow, right?
Yes, in the sense that maybe they come later to your mind.
But you mentioned the notes.
Yes,
so...
we have these notes that are on a strange book. So I don't remember the book. I'm sorry. And but the notes are like proximal gradient algorithms for machine learning and imaging that are by Saverio Salzo and myself, and more or less are the notes that we developed in the time for a PhD course we were offering at the University of Genova, and where we gathered more or less these things. So there is more than what I said today in these days, and maybe less on this last stuff, because yes, I can put them.
Okay. Yeah.
Oh, yes.
Okay, yeah, or the slides.
So
I have also the slides of.
Don't archive yet, we should, and they are on ResearchGate, I think, by the way.
Okay. Yeah. I can ask Saverio tomorrow, maybe. Okay, perfect. Again, do you have questions? Yes? Thank you.
Maybe this is also a bit more philosophical, but I'm curious because you mentioned before that there are results that say that you can prove a lower bound for the convergence of some algorithm. But so if you find an algorithm that is reach this fast, what could you study more about this problem? What you are interested to?
Okay, so maybe there are two things. One, in a sense, in some sense, it's true. So once you found an optimal algorithm, you are done. In
Okay.
the sense that you know that you cannot do better. On the other hand, all these lower bounds are worst case convergence results. So you know that on the worst function in the class, you will behave like this. So the idea is that you can try, for instance, to identify specific subclasses on which maybe you can find more refined algorithms, or you can show that your algorithm has better convergence results. This is the case for KL, for the Kaloyasiewicz. There has been a lot of work on this. And the other thing is that these complexity results, so I didn't want to enter into the details, but basically are like this. So you can show that if you are in RD, then you cannot, for instance, for the gradient methods, you cannot do better than 1 over k square for the first d-halves iterations. Okay. So this means that this is reasonable because when you apply a first order method, you imagine to be in a very high dimensional case. So you imagine to do a number of iterations which is similar to the dimension. But in practice, this thing does not tell you anything about the asymptotic convergence of your algorithm on a specific problem, right? So in the sense, these are even a bit less strong than as I stated them. Okay. This is the narrative. So this is the story that you always say because it's nice.
Okay.
And it's in a sense true.
Okay. The fact is that
the
fact is that in the long run, I could reach a better convergence.
Yeah, for instance, I didn't write it, but for accelerated gradient method, on each function you are a small O of 1 over k square, which in a sense contradicts the lower bound.
Okay.
Which is a big O of 1 over k square.
Okay. Thank you.
Okay, so let's thank Professor Villa again.